So here is something worth sitting with tonight. Something that might genuinely change how you think about the room you are lying in right now. The phone you might still be holding, or the lamp on your nightstand, or the faint glow of a street light coming through your window. That light is not arriving as a smooth, steady stream. It is arriving as individual particles, tiny, discrete packets of energy, each one landing on your retina one at a time, so fast that it looks continuous. The way a garden hose looks like a solid arc of water, even though it is really just billions of individual molecules. Each one of those packets of light is called a photon. And a photon does something that no object in your everyday experience does. It behaves like a wave when you are not looking at it, and like a particle when you are. Both descriptions are true. Neither one is complete. And nobody, not a single physicist alive today, can tell you what a photon actually is between the moment it leaves the lamp and the moment it hits your eye. That is quantum mechanics. And if it sounds strange, that is because it is strange. It is in fact the strangest collection of ideas that human beings have ever been forced to accept about the universe. And the key word there is forced. Because quantum mechanics was not invented by people who wanted the world to be weird. It was dragged into existence, experiment by experiment, by people who desperately wanted the world to make sense in the way they were used to, and who kept discovering, to their increasing dismay, that it did not. There were 6 of those experiments, 6 moments spread over about 30 years, where nature looked at our most cherished assumptions about how reality works and said, very quietly, no. And each time the physicists who confronted those results had to give something up. Something they had believed was obvious. Something that felt so fundamental it barely seemed worth questioning. And each time, what they found on the other side was not chaos or nonsense, but something far more unsettling. A deeper order, a more precise description of reality, one that happened to violate nearly every intuition that human beings had built up over 300 years of doing physics. Tonight, we are going to walk through all 6 of those experiments, slowly, from the very beginning. And I want to do it in a particular way. I want you to feel what the physicists felt when they first saw these results. Because the weirdness of quantum mechanics is not some abstract philosophical puzzle. It showed up in laboratories, in data, in numbers that did not add up. Real people stared at real instruments and realized that something was profoundly wrong with their picture of the world. And then, they had to figure out what to replace it with. And here is what I want you to sit with tonight. The warmth you feel right now, from the blanket on top of you, from your own body radiating heat into the room, that warmth is not flowing smoothly. It is arriving in tiny, discrete packets. Your skin is absorbing energy one quantum at a time, and each quantum is so small that the stream feels continuous. The way rain feels like a curtain of water, even though it is really individual drops. Why? Why does the universe deliver energy in chunks instead of pouring it like a liquid? A German physicist cracked that question open in the year 1900, and the answer unsettled him so deeply that he spent years trying to take it back. The light from your phone, from the street lamp outside, from the stars if your curtains are open, that light is hitting your eyes as individual particles. Each one is called a photon. And yet that same light, if you send it through 2 narrow slits, produces a wave pattern on the other side. The same stuff. Particles when it arrives, waves when it travels. How can the light touching your retina right now be both at once? A 26-year-old patent clerk figured out half the answer in 1905. Nobody believed him for almost 20 years. And those photons, on their way from the lamp to your eye,
They did not take a single path. According to the most successful theory in the history of science, each photon explored every conceivable route from the bulb to your retina. Paths that went straight, paths that bounced off the ceiling, paths that detoured to the sun and back, all of them simultaneously. The straight path you see is just the one that survived after the others cancelled each other out. Everything you have ever watched move in a straight line, every ball, every car, every beam of light, has secretly been exploring every other path at the same time. That sounds impossible. There is an experiment that proves it.
Now put your hand on the mattress beneath you. Feel how solid it is. That solidity is a quantum effect. The atoms in your hand and the atoms in the mattress are almost entirely empty space. If you removed all the emptiness, everything that makes up your body would fit inside a single grain of sand. You feel solid because the electrons in your skin refuse to overlap with the electrons in the fabric. And that refusal is governed by a quantum rule. But here is the unsettling part. Those electrons in your hand, do they have definite positions right now as you lie here? Classical physics says yes. Quantum mechanics says something far stranger. It says that certain properties of those electrons literally do not exist until something measures them. Not that we do not know where they are, that they do not have a where until the question is asked. And the atoms in your left hand and the atoms in your right hand, at some point in the history of the universe, some of them were entangled with particles that are now billions of miles away. Entanglement is a connection between particles that persists across any distance, instantly, in a way that Einstein called spooky and refused to accept. He was so sure it proved quantum mechanics wrong that he wrote a famous paper about it. 30 years later, someone designed an experiment to test his claim. The experiments have been done many times with increasing precision. Einstein was wrong. The connection is real. And it probably works across the entire observable universe. And then there is the deepest question, the one that all the others lead to. You are lying in a room made of atoms. Those atoms obey quantum mechanics. Every piece of technology around you, your phone, your light bulb, the GPS that guided you home, works because quantum mechanics works. The equations are settled. The predictions are confirmed. But what the theory actually says about the nature of the world you are lying in, what is really happening to those atoms when you close your eyes and stop looking at them, that question is still open. Right now, in 2026, the most brilliant physicists on the planet cannot agree on the answer. The most successful theory in the history of science, and the people who use it every day do not know what it is telling them about reality. Tonight, we are going to walk through the 6 experiments that forced these questions into the open, one by one, slowly. No rush at all. And if you drift off somewhere along the way, that is perfectly fine. The atoms in your body will keep obeying quantum mechanics whether you are awake or asleep. Let us begin with an oven. The experiment that proved energy comes in chunks. To understand why quantum mechanics exists at all, you have to put yourself in the mind of a physicist living at the very end of the 19th century. And what you would feel, overwhelmingly, is confidence, maybe even a little smugness. By 1895 or so, physics seemed very nearly complete. Isaac Newton had given the world mechanics and gravity more than 2 centuries earlier. James Clerk Maxwell had unified electricity and magnetism into a single, gorgeous set of equations in the 1860s, and in the process had revealed that light was an electromagnetic wave. Thermodynamics was understood. The periodic table was filling in nicely. The great edifice of classical physics stood tall and solid, and the general consensus among the people who had built it was that the big questions were mostly answered.
Albert Michelson, the American physicist who would later become famous for a very different reason, captured the mood perfectly in 1903 when he said that the more important fundamental laws and facts of physical science had all been discovered, and that future discoveries would have to be looked for in the 6th place of decimals. In other words, there was nothing left to find except finer and finer measurements of things we already understood. The architecture was done. All that remained was polishing. Now, you might think Michelson was being arrogant, and maybe he was, a little. But try to see it from his perspective. Over the previous 2 centuries, physics had pulled off some genuinely spectacular tricks. People had used Newton's laws to predict the existence of a planet, Neptune, that nobody had ever seen, purely from tiny wobbles in the orbit of Uranus. When they pointed their telescopes at the spot the math said the planet should be, there it was. If that is not a reason to feel confident about your theory of the universe, nothing is. But there were cracks, small ones, the kind that most people dismissed as loose ends, details that would eventually be cleaned up within the existing framework. And the most annoying of those cracks had to do with something incredibly mundane. It had to do with the way hot objects glow. You have seen this yourself, even if you did not think about it in these terms. A piece of metal in a blacksmith's forge starts out dark, and as it heats up, it begins to glow. First a dull red, then a brighter red, then orange, then yellow. And if you push it hot enough, a brilliant white. The color changes with the temperature, and the pattern is always the same, regardless of what the object is made of. A hot piece of iron glows the same color as a hot piece of copper at the same temperature. The material does not matter, only the temperature matters. This phenomenon is called blackbody radiation.
The name comes from the idea of a perfect emitter, an idealized object that absorbs all light that falls on it and radiates energy based purely on its temperature. In practice, physicists realized that the closest thing to a perfect blackbody was not a black surface at all. It was a hole. A small hole in a hollow metal box. Any light that shines into the hole goes in, bounces around inside the cavity, and eventually gets absorbed. Nothing comes back out. So the hole is a perfect absorber. And by the same logic, any radiation that the walls of the cavity emit, driven by the temperature of the metal, can escape through the hole unimpeded. So the hole is also a perfect emitter. If you heat the box and look at the light coming out of the hole, you see the pure spectrum of thermal radiation. And by the 1890s, experimentalists in Germany had measured this spectrum with extraordinary precision. They had beautiful, clean data, showing exactly how much energy was radiated at each wavelength for different temperatures. The curves were smooth and predictable. At low frequencies, low energy light, the radiation intensity climbed steadily. It reached a peak at some characteristic wavelength that depended on the temperature. And then it fell off steeply at higher frequencies, shorter wavelengths, more energetic light. The hotter the object, the more energy it radiated at every wavelength, and the peak shifted toward the blue end of the spectrum. That is why a warm object glows dull red, and a very hot object glows white. The peak has shifted so far toward the blue that the radiation covers the entire visible spectrum, and mixing all colors gives you white. Now, this was not just an abstract puzzle. Germany in the 1890s was industrializing rapidly. Electric lighting was the hot new technology, literally. The German Bureau of Standards, an institution called the Physikalisch-Technische Reichsanstalt, was actively funding research into thermal radiation because the lighting industry needed better standards. If you are manufacturing light bulbs, you need to understand how hot materials produce light. How do you maximize the visible light output of a filament at a given temperature? That is a practical question with real commercial value. So there was money behind this research, and some of the best experimental physicists in the world were working on it. The data were beautiful. The theory was a disaster. Here is what happened when physicists tried to explain the black-body spectrum using classical physics. They started from a reasonable picture. The walls of the cavity contain charged particles, electrons, that vibrate back and forth.
These vibrating charges emit electromagnetic waves, light, and those waves bounce around inside the cavity, creating standing waves, like the vibrations of a guitar string but in 3 dimensions. For any given wavelength, you can figure out how many distinct standing wave patterns fit inside the cavity. And for longer wavelengths, there are relatively few. But as you move to shorter and shorter wavelengths, the number of possible standing wave patterns grows rapidly. In 3 dimensions, the number of modes is proportional to the frequency cubed. Shorter wavelength, higher frequency, vastly more modes. Now, in classical physics, there is a beautiful principle called the equipartition theorem. It says that in thermal equilibrium, each mode of vibration gets the same average amount of energy. The energy is shared equally. So if you have twice as many modes at some frequency, you get twice as much total energy at that frequency.
And since the number of modes grows as frequency cubed, the energy radiated at each frequency should also grow as frequency cubed. This prediction is called the Rayleigh-Jeans law, after Lord Rayleigh and James Jeans, who worked it out carefully. And at long wavelengths, low frequencies, it matched the experimental data quite well. The theory and the measurements agreed, but as you moved to shorter wavelengths, higher frequencies, the prediction just kept climbing. Frequency cubed means that the energy goes up and up and up without limit. At ultraviolet frequencies, the predicted energy was already much higher than what the experiments showed. And at even shorter wavelengths, X-rays and beyond, the prediction went to infinity. Infinity. An infinite amount of energy radiated at short wavelengths from any warm object. Your coffee mug, sitting on your nightstand, should, according to this calculation, be blasting you with infinite X-ray radiation right now. Obviously, this is insane.
This prediction was so dramatically wrong, so catastrophically at odds with reality, that it got a suitably dramatic name: the ultraviolet catastrophe. On the other side of the spectrum, a formula proposed by Wilhelm Wien in Germany worked well at short wavelengths but failed at long ones. So there were 2 formulas, one that worked on the left side of the spectrum but blew up on the right, and one that worked on the right side but failed on the left. And nobody could figure out how to connect them. This is where Max Planck enters the story. And to understand what Planck did, you really need to understand who he was, because his personality is central to why his discovery was so reluctant, so painful, and ultimately so revolutionary. Planck was born in 1858 in Kiel, Germany. He came from a long line of professors, lawyers, and clergymen, solid, respectable, intellectually serious people. And Planck fit that mold perfectly.
He was orderly, traditional, deeply conservative in his thinking. He loved thermodynamics with a passion that bordered on devotion. He believed in absolute laws of nature, in a rational, comprehensible universe governed by principles of elegant simplicity. He was not the kind of person who would cheerfully tear up the foundations of physics. He was exactly the kind of person who would exhaust every conceivable conventional approach before even contemplating something radical. And there is a beautiful irony in the fact that one of his professors, Philip von Jolly, actually advised the young Planck against going into physics, telling him that the field was essentially complete and that there was nothing important left to discover. Planck, according to his own account, replied that he did not want to discover new things. He just wanted to understand the existing foundations more deeply. A conservative man, attracted to a field he believed was finished, seeking only to understand what was already known. This is the person who would blow a hole in classical physics that the field has never recovered from. By 1897, Planck was a professor in Berlin, and for the next 3 years he threw himself at the blackbody problem with the tenacity and methodical patience that defined his character. He tried every approach he could think of. He tried to derive the spectrum from the fundamental principles of thermodynamics and electromagnetism. He tried different assumptions about how the oscillators in the cavity walls emitted and absorbed radiation. He tried, and nothing worked. And then, on October 19th, 1900, we know the exact date because the records of the German Physical Society are meticulous. Planck presented a new formula. He had found a mathematical expression that smoothly connected the Rayleigh-Jeans prediction at long wavelengths with Wien's formula at short wavelengths. It matched the experimental data across the entire spectrum. Perfectly. Not approximately, not roughly. The agreement was extraordinary. One of the experimentalists in the audience, Heinrich Rubens, went home that evening and compared Planck's formula against his latest measurements. The next morning, he called Planck to tell him the formula was exact. But here is the thing about Planck's formula. He had it, but he did not know why it worked. He had the right answer, but no derivation, no physical justification. He had guessed it, or more precisely, he had interpolated it. He had found a mathematical form that bridged two known limits, and that bothered him enormously. Planck was not the kind of person who could live with a formula that worked for no reason. He needed to understand why. So over the next 2 months, he worked backward. He asked himself, what physical assumption would I need to make about the oscillators in the cavity walls to derive this formula from first principles? What assumption about how energy is emitted and absorbed would give me this exact mathematical expression? And what he found disturbed him deeply. The only way to make the math work was to assume that the oscillators in the walls could not emit or absorb energy in arbitrary amounts. They could only emit or absorb it in discrete chunks, specific, indivisible packets. He called these packets quanta, from the Latin word for how much. And the size of each quantum was not arbitrary. It depended on the frequency of the radiation. Higher frequency light came in bigger chunks. Lower frequency light came in smaller chunks. The relationship was simple. The energy of one quantum equals the frequency of the light multiplied by a new constant, a tiny number that Planck called h. Think about what this means. In classical physics, energy is smooth. It is continuous. You can have any amount of it. It is like water. You can pour half a glass, or a third, or any fraction you like, as fine-grained as you please. What Planck was saying is that at the atomic level, energy is more like sand. From a distance, it looks perfectly smooth and continuous, but up close, it comes in individual grains, and you cannot have half a grain. And this assumption, this seemingly small mathematical tweak, solved the ultraviolet catastrophe. Here is why. At long wavelengths, low frequencies, the energy of one quantum is very small. So even at modest temperatures, the oscillators in the cavity walls have plenty of energy to emit these small quanta. The spectrum builds up freely, and it matches the classical Rayleigh-Jeans prediction. But at shorter wavelengths, higher frequencies, the energy of a single quantum becomes larger and larger. And at some point, the quantum is so big that most of the oscillators simply do not have enough energy to emit even one. They are like people trying to climb a staircase where the steps are 10 feet tall. They cannot get up there. So the amount of radiation at those high frequencies drops off, exactly as the experiments showed, instead of climbing to infinity. The ultraviolet catastrophe disappears because at high frequencies, the price of admission, 1 quantum, is too high for most oscillators to pay. Planck presented this derivation on December 14, 1900, to the German Physical Society. And that date, December 14, 1900, is often cited as the birthday of quantum mechanics. But it is worth pausing on the fact that the father of quantum mechanics did not believe in what he had just done. Planck himself considered the quantum hypothesis a mathematical trick, a computational shortcut. He called it, in his own words, an act of desperation. He had tried everything else, and nothing worked. The quantum assumption was a last resort, and he fully expected that someone, sooner or later, would find a proper classical explanation that gave the same answer without the need for this bizarre discreteness of energy. He spent years afterward trying to undo his own discovery. He tried repeatedly to derive his formula using only classical physics. He never succeeded. And the number itself, Planck's constant, the quantity h, is astonishingly small. It is about 6.626 times 10 to the minus 34 joule seconds. Written out, that is a decimal point followed by 33 zeros and then a 6. It is so tiny that in our everyday world, the graininess of energy is completely invisible. The individual quanta are so small that energy looks perfectly smooth to us, just like a sandy beach looks smooth from an aeroplane, even though it is made of individual grains. But at the atomic scale, that graininess matters enormously. It changes everything. And here is the detail that connects back to everything that follows. Planck's constant has units of energy times time, joule seconds. That combination of units has a name. It is called action. Planck's constant is a quantum of action, the smallest possible unit of this quantity that governs how physical systems evolve. We will come back to that idea later, because it turns out to be far more central to the story than anyone realized in 1900. Action is the thread that runs through all of quantum mechanics, the single quantity that separates the quantum world from the classical one. When the action involved in a physical process is comparable to Planck's constant, quantum effects dominate. When the action is much larger than Planck's constant, the system behaves classically, and the quantum graininess disappears beneath the smooth surface of everyday experience. So that is where things stood at the turn of the century. A conservative German professor had introduced a radical idea that he did not believe in, to solve a practical problem about how hot objects glow. The idea worked perfectly, and the number at its heart, 6.626 times 10 to the minus 34, would turn out to be arguably the most important constant in all of physics. But Planck himself thought it was temporary, a patch, a mathematical convenience that would eventually be replaced by something more sensible. Now, let me take you a little deeper into the physics here, because the actual mechanism by which Planck's quantum hypothesis eliminates the ultraviolet catastrophe is worth understanding carefully. It is one of those cases where the math reveals something that pure intuition misses. In classical physics, the equipartition theorem gives each mode of vibration the same average energy, kT, where K is Boltzmann's constant and T is the temperature. It does not matter whether the mode is a low-frequency vibration or a high-frequency one. Each mode gets the same share. This is deeply democratic and completely wrong at high frequencies. Planck's assumption changes this picture in a subtle but devastating way. If energy can only come in chunks of size h times f, then for a low-frequency mode, the chunk size is very small. It takes very little energy to excite this mode by 1 quantum. At room temperature, the thermal energy available to each oscillator, roughly kT,
is much larger than the quantum hf, so the oscillator can absorb and emit many quanta. It behaves almost classically, and the average energy per mode is still approximately kT. The Rayleigh-Jeans formula works fine here. But as the frequency increases, the chunk size hf grows. At some frequency, the energy of a single quantum becomes comparable to kT, and beyond that frequency, hf is larger than kT, much larger. Now the oscillator needs more energy to emit even one quantum than thermal fluctuations typically provide. Most of the time, the oscillator just sits there, unable to participate. It is like trying to climb a staircase where each step is taller than you can reach. You stand at the bottom, unable to get up. So instead of each mode getting the same average energy, the high-frequency modes get almost no energy at all. They are frozen out. The radiation spectrum climbs at low frequencies, following the classical prediction, but then turns over and falls as the quantum effects kick in and the high-frequency modes go silent. The peak of the spectrum, where the competition between the growing number of modes and the shrinking ability to excite them produces the maximum radiation, shifts to higher frequencies at higher temperatures. This is Wien's displacement law, and it falls out of Planck's formula naturally. And the total energy radiated at all frequencies is finite.
There is no catastrophe.
The infinity has been tamed by the simple requirement that energy comes in discrete packets. One more detail about Planck that I want to mention, because it tells you something about the human cost of scientific revolutions. Planck's personal life was marked by a staggering amount of tragedy. His first wife died young, his eldest son was killed in World War I, his twin daughters both died in childbirth 2 years apart. And during World War II, his youngest son Erwin was implicated in the plot to assassinate Hitler and was executed by the Gestapo in January 1945, just months before the war ended. Through all of this, Planck kept working. He remained in Germany through the Nazi period, trying to preserve what he could of German science from within, a position that was morally ambiguous and personally agonizing. He met with Hitler in 1933 to plead for the retention of Jewish scientists and was rebuffed. He was, by all accounts, a profoundly decent man trapped in profoundly indecent times. He died in 1947 at the age of 89, having lived long enough to see the quantum revolution he had started transform every branch of physics. Whether that revolution gave him satisfaction or sorrow is not entirely clear from the historical record. He had, after all, spent years trying to undo it. The constant that bears his name, that tiny number, 6.626 times 10 to the minus 34, is carved into his tombstone in Göttingen. 5 years later, a 26-year-old patent clerk in Switzerland would pick up Planck's idea and push it in a direction that Planck himself would never have gone. And in doing so, he would shatter the second great assumption of classical physics, the wave nature of light, and open a door that could never be closed again.
The experiment that proved light comes in particles. To understand why Einstein's paper on the photoelectric effect was so radical, you first have to appreciate just how thoroughly, how overwhelmingly, the wave theory of light had been established by 1905. This was not a tentative hypothesis. This was one of the most successful theories in the entire history of physics. Thomas Young had demonstrated interference patterns in his famous double-slit experiment back in 1801, bright and dark bands that only make sense if light is a wave, with crests and troughs that reinforce or cancel each other. Maxwell's equations, from the 1860s, had unified electricity and magnetism and predicted electromagnetic waves that traveled at exactly the speed of light. The match was too perfect to be coincidence. Light was an electromagnetic wave. Diffraction, polarization, interference, refraction. Every optical phenomenon anyone had ever studied
confirmed it.
This was settled science in the deepest possible sense. And yet, there was this one experiment, a small, puzzling experiment that had first been noticed back in 1887 by Heinrich Hertz, the same Hertz whose name we use for the unit of frequency, cycles per second. Hertz had observed that when ultraviolet light shines on a metal surface, the metal emits electrons. The light knocks them right out of the surface. This phenomenon was called the photoelectric effect, and on its face it did not seem terribly mysterious. Light carries energy. If you pour enough energy into a metal, electrons can escape. Perfectly reasonable. But when people began measuring the details, and this is where the trouble started, the details made no sense. The key experiment works like this. You have a metal plate inside a vacuum chamber. You shine light on it, and electrons come flying off.
These electrons cross a gap to another metal plate on the other side, and you connect the two plates to a battery that opposes the electron flow. You increase the voltage on the battery until the electrons can no longer make it across the gap. They are being pushed back by the electric field. The voltage at which you just barely stop the electrons is called the stopping voltage, and it tells you how much kinetic energy the fastest electrons had when they left the surface. Now think about what classical physics predicts. Light is a wave. The energy carried by a wave depends on its amplitude, the height of the wave, the intensity of the light. A brighter light means bigger electromagnetic fields, and bigger fields should push harder on the electrons in the metal and give them more energy. So if you increase the brightness, the stopping voltage should go up, because the electrons should be flying off with more energy. What about the frequency, the color of the light?
Well, classically, changing the frequency does not change the amplitude of the wave. A dim violet light and a dim red light can have the same amplitude. So changing the frequency should not affect the energy of the electrons. The stopping voltage should stay the same. Here is what actually happens. It is essentially the opposite. When you increase the brightness of the light, the stopping voltage does not change. The electrons come off with exactly the same maximum energy. You just get more of them. Brighter light ejects more electrons, but each individual electron has the same energy as before. And when you change the frequency? When you switch from red light to blue light to ultraviolet, keeping the brightness the same, the stopping voltage changes. Higher frequency light produces higher energy electrons, and below a certain threshold frequency, which depends on the metal you are using, no electrons come out at all, no matter how bright the light is.
You can blast the metal with the most intense red light you can produce, and nothing happens. Not a single electron escapes. But switch to dim ultraviolet light, even barely visible amounts of it, and electrons start popping off immediately. This was deeply puzzling, and the classical wave picture could not explain it. If light is a smooth, continuous wave, then a bright enough wave should eventually deliver enough energy to free an electron, regardless of frequency. Think of it like waves hitting a beach. If you wait long enough, even gentle waves will eventually move a pebble. But that is not what happens with the photoelectric effect. Below the threshold frequency, no amount of waiting helps. No amount of brightness helps. The electrons simply will not come out. Einstein's explanation, published in 1905, was so simple and so elegant that it is almost shocking it took so long for anyone to propose it. He said, "What if light is not just emitted and absorbed in chunks, the way Planck had suggested? What if light itself, traveling through space, exists as individual particles? What if each particle of light, each photon, carries an energy that depends on its frequency? One photon, one chunk of energy equal to Planck's constant times the frequency. E equals h times f. If that is true, then the photoelectric effect becomes perfectly clear. When a photon hits an electron in the metal, it is a one-on-one interaction. One photon delivers its energy to one electron. If the photon carries enough energy, more than the binding energy holding the electron in the metal, the electron escapes. Whatever energy is left over becomes the kinetic energy of the electron, its speed. That leftover energy is what determines the stopping voltage. Now everything falls into place. Brighter light means more photons, not more energetic photons.
More photons eject more electrons, but each electron gets the same amount of energy from each individual photon, so the stopping voltage does not change with brightness. Higher frequency light means each photon carries more energy because E equals h times F. So the electrons come off with more kinetic energy and the stopping voltage increases with frequency. And below the threshold frequency, each photon simply does not carry enough energy to free an electron. 1,000 weak punches do not add up to one strong one. Each photon acts alone, and if it is too weak, the electron stays put. Einstein wrote up this explanation in a paper that was, on the surface, about a fairly obscure experimental effect. The photoelectric effect was not the kind of thing that made headlines, but lurking inside that paper was a claim so bold, so radical, that even the man who had started the quantum revolution, Max Planck himself, thought Einstein had gone too far. Because here is the thing. Planck had quantized the oscillators in the walls of the black body cavity. That was a statement about matter, about how atoms emit and absorb energy. Einstein was quantizing light itself. He was saying that electromagnetic radiation, this thing that Maxwell had shown so beautifully to be a continuous wave, actually has a particle-like nature. It comes in lumps, and those lumps travel through space like tiny bullets, each one carrying a specific, discrete amount of energy. This was not just a tweak to classical physics. This was a direct contradiction of one of the most well-established theories in all of science. Maxwell's equations describe light as oscillating electric and magnetic fields, continuous wave phenomena spreading through space. And now Einstein was saying that these waves were also, somehow, particles. Both descriptions were true. Both were needed, and nobody could explain how that was possible. The physics community, by and large, was not impressed. Planck himself, when he later wrote a letter recommending Einstein for membership in the Prussian Academy of Sciences, praised Einstein's many contributions, but specifically noted that Einstein had sometimes missed the target in his speculations, and he cited the light quantum hypothesis as an example. Planck was essentially saying, "Great physicist, brilliant mind, but that photon business is probably wrong." It was not wrong. It was one of the most important ideas in the history of physics. And when Einstein eventually won the Nobel Prize in 1921, it was not for relativity, not for E equals mc squared, not for any of the things that made him a household name. It was for this, for explaining the photoelectric effect, for showing that light comes in particles. The Nobel Committee felt safer rewarding the photoelectric work, which had clear, unambiguous experimental support, than touching the still controversial theory of relativity. And that is worth pausing on. The idea that light is made of particles was so controversial that even 16 years after Einstein proposed it, the Nobel Committee chose it specifically because it was the least controversial of his achievements. It had been experimentally verified. You could not argue with the data, but accepting the data meant accepting something genuinely disturbing, because now you had a full-blown paradox sitting right in the middle of physics. Light is a wave. The evidence for that is overwhelming. A century of experiments, from Young's double slit to Maxwell's equations to diffraction and polarization, had confirmed it beyond any reasonable doubt. And light is a particle. Einstein had shown that. The photoelectric effect demanded it. Both of these things are true. and they seem completely contradictory. A wave is extended in space, oscillating, spread out. A particle is localized, compact, discrete. How can something be both? This is the first deep strangeness of quantum mechanics.
It is called wave-particle duality.
And when you first encounter it, there is a natural tendency to think that it must be some kind of misunderstanding, or that physicists are being sloppy with their language. They are not. The universe genuinely works this way. And the discomfort you feel when you try to picture it is the same discomfort that the greatest physicists of the early 20th century felt. The Danish physicist Niels Bohr, who we will meet shortly, eventually argued that you simply cannot ask what light really is between measurements. It is not a wave pretending to be a particle, or a particle pretending to be a wave. It is something else entirely, something that does not have a name in everyday language, something that shows you one face or the other, depending on how you choose to look at it. But in 1905, all of that philosophical reckoning was still years away.
What mattered right then was that two seemingly contradictory things were both experimentally true, and nobody knew how to reconcile them. Let me stay with this moment a little longer, because the wave-particle duality of light was genuinely revolutionary, and the full implications took decades to sink in. When Einstein proposed that light comes in discrete packets, he was not saying that light is only a particle. He was saying that under certain circumstances, when light interacts with matter at the atomic level, its behavior is best described as particle-like. The photon carries a definite energy, h times f, and delivers it to a single electron in a single interaction. The wave picture, in which energy is distributed smoothly and continuously across an electromagnetic field, cannot account for this. But the wave picture remains essential for other phenomena. Interference, diffraction, polarization, none of these make any sense if light is just a stream of little bullets.
Bullets do not interfere with each other. Bullets do not bend around corners. Bullets do not polarize. Waves do. So you need both. And from 1905 onward, physicists had to learn to live with the deeply uncomfortable idea that light is both wave and particle, not one or the other, not wave sometimes and particle other times, both, always, simultaneously, with different aspects revealing themselves in different experimental contexts. This sounds like it should be a contradiction, and it would be if you insist on thinking of waves and particles as they appear in everyday life. An ocean wave is extended, spread out, continuous. A baseball is compact, localized, discrete. These are completely different kinds of things. How can something be both? The answer that quantum mechanics eventually provided, is that photons are neither waves nor particles in the everyday sense. They are quantum objects, a category of thing that has no analog in ordinary experience.
Quantum objects exhibit wave-like behavior when they are propagating through space, and particle-like behavior when they are interacting with matter. But between propagation and interaction, between emission and absorption, the quantum object is described by a wave function, a mathematical object that encodes probabilities, not a physical wave in any classical sense. This idea, which seems natural to physicists today after a century of working with it, was profoundly disorienting in 1905. And it raised a question that nobody could answer at the time. If light has this dual nature, does matter have it too? The question would hang in the air for nearly 20 years, until a French prince answered it in 1924. But before we get there, we need to understand why the question was so urgent, and that brings us to the structure of the atom. Now, I should mention something about how this period felt to the people living through it. Because from our perspective, looking back, The history of quantum mechanics can seem like a smooth progression of insights building on each other. Planck discovers the quantum, Einstein extends it to light, Bohr applies it to the atom, de Broglie extends it to matter, Heisenberg and Schrödinger formalize it. Each step leads logically to the next. But at the time, it did not feel like that at all. It felt like chaos. It felt like the rules of physics were breaking down, and nobody knew what to replace them with. There were bitter disagreements, false starts, abandoned ideas, competing formalisms, and deep personal rivalries. The photograph taken at the 1927 Solvay conference in Brussels, which shows 29 of the most brilliant physicists of the century gathered in one room, is often held up as a monument to collective genius. And it was.
But it was also a monument to collective confusion. The people in that photograph disagreed with each other about the most fundamental questions in physics, and many of those disagreements persisted for the rest of their lives. Einstein is there, sitting in the front row next to Lorentz, arms crossed, looking skeptical. Bohr is standing in the middle, looking earnest and slightly worried. Heisenberg is in the back row, young and intense. Schrödinger is there too, elegant and somewhat aloof. Dirac is next to him, characteristically silent. Marie Curie sits in the front row, the only woman in the photograph, looking directly at the camera with a gaze of startling intensity. And every single one of these people is struggling with the same questions. What is the wave function? What happens when you measure something? Does God play dice? Is quantum mechanics a complete theory or an approximation of something deeper? These were not abstract questions for them. They were existential questions about the nature of reality.
And the people in that photograph knew they were the ones who had to answer them. They did not agree. They never fully agreed. And nearly 100 years later, we still have not settled the argument they started. But I am getting ahead of the story. Let us go back to the atom. And meanwhile, something else was happening. Something that was about to push the quantum revolution from light into matter itself, into the very structure of the atom. Because around the same time Einstein was rethinking the nature of light, other physicists were discovering that atoms, those supposedly indivisible building blocks of everything, had an internal structure that was far stranger than anyone had imagined. And when they tried to understand that structure using classical physics, they hit a wall. Not a small wall, a devastating one. According to everything classical physics knew about electromagnetism, atoms should not exist at all. They should destroy themselves in a fraction of a second. And the person who found a way around that impossibility, who saved the atom from classical self-destruction, was a quiet, thoughtful Dane who would become one of the most influential and controversial figures in the entire history of physics. The experiment that proved particles take every route at once. Before we get to the most mind-bending experiment in all of physics, we need to take a detour through the atom. Because the double-slit experiment, the experiment that will show us that particles travel through all possible paths simultaneously, only makes sense once you understand what matter itself turned out to be, and how deeply strange that revelation was. By 1911, physicists knew that atoms existed. They knew atoms contained electrons, those tiny negatively charged particles that J.J. Thomson had discovered in 1897. But nobody knew how atoms were actually structured.
Thomson's model,
the so-called plum pudding model, imagined electrons embedded in a diffuse blob of positive charge, like raisins scattered through a pudding. It was a reasonable guess. Nobody had any way to look inside an atom. Then Ernest Rutherford set up an experiment that changed everything. Rutherford was a New Zealander working in Manchester, England. A big personality, booming voice, hands-on in the lab, in a way that many theoretical physicists of his era were not. He and his collaborators, Hans Geiger and Ernest Marsden, fired tiny, fast-moving alpha particles, essentially helium nuclei, positively charged bullets, at a sheet of gold foil so thin you could see light through it. If Thomson's plum pudding model were right, if the positive charge were spread out evenly across the whole volume of the atom like a soft cloud, then the alpha particles should punch right through with only slight deflections. Like bullets through fog, and most of them did.
Most of the alpha particles sailed straight through the gold foil as if it were not even there. But some of them bounced back. Not just deflected a little, bounced almost straight back toward the source. Rutherford later described his reaction in one of the most famous quotes in the history of physics. He said it was as if you had fired a 15-inch artillery shell at a piece of tissue paper, and it came back and hit you. The only explanation was that almost all of the atom's mass and all of its positive charge was concentrated in a fantastically tiny region at the center. Rutherford called it the nucleus. The numbers were staggering. The nucleus was roughly 10,000 times smaller than the atom itself. If you scaled an atom up to the size of a football stadium, the nucleus would be a marble sitting at the center of the field. The rest of the atom, all that space where the electrons supposedly lived, was essentially empty. The atom, this fundamental building block of all matter, the thing that makes up your body and the bed you are lying on and the air you are breathing, is almost entirely nothing. But Rutherford's model had a fatal flaw, and the flaw was not subtle, it was lethal. If you have a positive nucleus at the center and negative electrons somewhere around it, you need some reason for the electrons not to fall straight in. Opposite charges attract. So the obvious idea, the one Rutherford implicitly assumed, was that the electrons are orbiting the nucleus, the way planets orbit the sun. The centripetal acceleration balances the electromagnetic attraction, and the electrons stay in stable orbits. The problem is that Maxwell's equations, those same beautiful equations that had unified electricity and magnetism, said very clearly that any charged particle that accelerates must radiate energy. And an electron moving in a circle is constantly accelerating because its direction is constantly changing. So a classically orbiting electron should continuously radiate electromagnetic waves, losing energy as it goes, spiraling closer and closer to the nucleus, until within a tiny fraction of a second it crashes in. The atom should destroy itself almost instantly. Every atom in the universe should have collapsed long ago. Obviously they have not. You are here. The stars are burning. Chemistry works. Something was profoundly wrong with the classical picture. This is where Niels Bohr enters the story. Bohr was Danish, born in Copenhagen in 1885. His father was a physiology professor. His mother came from a wealthy banking family, and the household was deeply intellectual.
Bohr had a younger brother, Harold, who was a brilliant mathematician, and also, wonderfully, an Olympic soccer player. He played for the Danish national football team, which is a real fact that has nothing to do with quantum mechanics, but is too good to leave out. Bohr himself was quiet, thoughtful, and famously slow to reach conclusions. He would turn a problem over and over, approaching it from every angle, and he often expressed his ideas in language so carefully hedged that people could not always tell what he was saying. But when he got there, he was usually right. In 1913, confronted with the impossible instability of Rutherford's atom, Bohr did something audacious. He did not try to fix classical physics. He did not look for some clever mechanism within Maxwell's equations that might stabilize the orbits. Instead, he said, "Classical physics does not apply here. The rules are different." And then he made up new rules.
He declared that electrons could only orbit the nucleus at certain specific distances, certain allowed orbits. In these orbits, and only these orbits, the electron simply does not radiate energy. It just orbits, stably, indefinitely. Not because there is some classical mechanism preventing the radiation, but because that is how the quantum world works. He imposed this as a postulate, an axiom, a rule from outside classical physics. And the rule he used to determine which orbits were allowed brought Planck's constant right back into the center of the story. Bohr said that the angular momentum of the electron, the quantity that describes how much rotational motion it has, could only take certain discrete values, whole number multiples of Planck's constant divided by 2 pi. 1 unit, or 2 units, or 3, but never 1.5, never 2.7. The angular momentum was quantized. When Bohr calculated the energy levels of his allowed orbits for hydrogen, and then calculated the frequencies of light that would be emitted when electrons jumped between those levels, the numbers matched the known spectral lines of hydrogen with extraordinary precision. For decades, scientists had known that heated hydrogen gas emits light at very specific wavelengths. A red line, a blue-green line, a violet line, with darkness in between. A Swiss schoolteacher named Johann Balmer had found a simple mathematical formula that predicted these wavelengths, but nobody knew why it worked. Bohr's model explained it. The pattern fell out of the mathematics naturally, but here is what was deeply unsatisfying about Bohr's model. It worked spectacularly well for hydrogen. 1 electron, 1 proton, the simplest atom. When physicists tried to extend it to helium, with 2 electrons, it failed. And the whole thing rested on these arbitrary rules. Why these orbits? Why does the electron not radiate in them? What is the underlying reason? The answer came from a French aristocrat with a wild idea. Louis de Broglie, a prince from one of France's most prominent families, had originally studied history before switching to physics. And in his doctoral thesis, submitted in 1924, he asked a question so audacious that his thesis committee was not sure whether it was brilliant or insane. His question was this: if light, which everyone had treated as a wave, also behaves like a particle, which is what Einstein showed with photons, then should the reverse not also be true? Should matter, which everyone treats as particles, also behave like waves? And he did not just suggest this vaguely. He wrote down a formula. He said the wavelength of any particle is equal to Planck's constant divided by the particle's momentum. Lambda equals h over p. There is that constant again, Planck's tiny number, bridging the particle description and the wave description. For anything you can hold in your hand, a baseball, a grain of sand, the mass is so large compared to Planck's constant that the wavelength comes out absurdly small, trillions of times smaller than a proton. You would never notice it. But for something as light as an electron, the wavelength turns out to be on the order of the size of an atom. And that changes everything, because now Bohr's quantized orbits had a physical explanation. If an electron is a wave, and it is wrapped around a nucleus in a circular orbit, then that wave has to close on itself. It has to form a standing wave, the way a guitar string vibrates only at certain frequencies because the ends are fixed. The circumference of the orbit has to be a whole number of wavelengths. 1 wavelength, 2, 3, but never 1.5.
If the wave does not fit, it interferes with itself destructively and cancels out. When you work out the math, the orbits where the wave fits are exactly the orbits Bohr had postulated. The quantization of angular momentum is not some mysterious decree. It is a natural consequence of electrons being waves. De Broglie's thesis committee, uncertain about what to make of it, sent a copy to Einstein. Einstein reportedly replied that de Broglie had lifted a corner of a great veil. The thesis was accepted.
de Broglie won the Nobel Prize for it in 1929. Let me go further into the strange world of the quantum atom, because the transition from Bohr's model to full quantum mechanics involved some of the most creative and anguished thinking in the history of science. Bohr's model, with its quantized orbits and discrete energy levels, was a spectacular success for hydrogen. But physicists quickly realized that it was not really a proper theory.
It was more like a set of ad hoc rules grafted onto classical mechanics. The electron was still imagined as a little ball orbiting a nucleus, following a definite path in space. The only quantum element was the restriction on which orbits were allowed, and the model had no mechanism for explaining transitions. Bohr could tell you the energy levels, but he could not tell you how long the electron spent in each one, or when it would jump, or why. He could tell you the frequency of the photon emitted during a jump, but he could not tell you the intensity, how bright each spectral line would be. And for any atom more complex than hydrogen, the model failed to give accurate predictions. What was needed was a complete replacement of classical mechanics at the atomic scale. Not a modification, not a patch, a new theory. And that theory arrived in two dramatically different forms in the span of less than a year, 1925 to 1926.
That new theory arrived in two dramatically different forms. The first came from Werner Heisenberg, a young German physicist who retreated to a rocky, almost barren island in the North Sea called Heligoland to escape a crippling bout of hay fever, and there, working alone through the nights, constructed an abstract algebraic framework called matrix mechanics. It was brilliant but austere, pure math, no pictures, no attempt to visualize what the electron was doing. The second approach came from Erwin Schrödinger, and the contrast between the two men and their two methods is one of the great stories in physics. Schrödinger was Austrian, born in Vienna in 1887. He was cultured, charming, multilingual, and by all accounts extraordinarily charismatic. He had wide interests: philosophy, literature, Eastern mysticism, and a personal life that was, to put it diplomatically, unconventional.
He had long-term simultaneous relationships with multiple women, a fact that occasionally complicated his academic career but did not noticeably diminish his scientific output. In late 1925, Schrödinger went on a Christmas vacation to the Swiss Alps. He stayed at a villa in Arosa, a resort town above the clouds, and he brought with him de Broglie's thesis about matter waves. He also brought a companion, a woman whose identity has never been definitively established. History records only that she was not his wife. Over the course of 2.5 weeks, in that alpine villa, Schrödinger derived his equation. He started from de Broglie's idea that particles have wavelengths, and he asked, what wave equation would such a matter wave satisfy? What differential equation governs how these waves evolve in space and time? The Schrödinger equation, he found, is in some ways deceptively simple. It says that the rate of change of the wave function with respect to time is proportional to a certain combination of its spatial derivatives and the potential energy. It is a linear partial differential equation, the kind of equation that physicists had been solving for more than a century in the context of heat flow, sound waves, and electromagnetism. The tools were familiar. The methods were well established. And when Schrödinger applied his equation to the hydrogen atom, when he wrote down the wave function, applied the appropriate boundary conditions, and solved, the energy levels dropped out automatically. The same levels Bohr had found, the same levels Heisenberg's matrix mechanics produced. But now they came from a beautiful, continuous, visualizable wave equation, rather than from abstract matrices or arbitrary quantization rules. The physics community, by and large,
loved Schrödinger's approach and distrusted Heisenberg's. Schrödinger's wave mechanics was intuitive. You could picture the wave function. You could draw it. You could use familiar mathematical tools to work with it. Heisenberg's matrix mechanics, by contrast, was abstract and algebraic, and most physicists were not comfortable with infinite dimensional matrices. But the two theories were mathematically equivalent. Schrödinger himself proved this in 1926. Every problem you can solve with wave mechanics, you can solve with matrix mechanics, and vice versa. They are different languages for describing the same physics, the way French and English are different languages for describing the same world. The choice between them is a matter of convenience and taste, not truth. What they did not agree on was the interpretation. Schrödinger believed his wave function represented something physically real, perhaps the charge density of the electron, smeared out in space like a cloud.
Heisenberg believed that the only real things were the observable quantities, the frequencies and intensities of spectral lines, and that the wave function was just a mathematical tool for predicting them. And then Born came along and said the wave function gives you probabilities. Not charge densities, not physical waves, but odds. The probability of finding the electron at a particular location if you look. Schrödinger was horrified. He later said that if he had known his equation was going to be interpreted this way, he would have preferred never to have been involved with quantum mechanics at all. But Born's interpretation survived because it worked. It gave the right answers for everything. The wave function, squared, gives you probabilities, and those probabilities match experiment with astonishing accuracy.
Whether the wave function is real in some deeper sense, whether it describes something that exists independently of measurement, remains one of the great open questions, the question that separates the different interpretations of quantum mechanics, the question we will confront in the final chapter. For now, though, what matters is that by 1926, the mathematical framework of quantum mechanics was essentially complete. The Schrödinger equation, or equivalently Heisenberg's matrix formulation, supplemented by Born's probabilistic interpretation, gave physicists a theory that could in principle predict the behavior of any atomic or subatomic system. And over the following years, as Dirac combined it with special relativity and the theory of quantum electrodynamics was developed, its predictive power only grew. But the philosophical questions, the questions about measurement, about reality, about what the wave function means, those questions did not go away. They were pushed to the side, dismissed as merely philosophical by pragmatically minded physicists who were too busy making predictions and building bombs and designing transistors to worry about metaphysics. Shut up and calculate, as the saying goes. And maybe that was the right strategy for a while. The theory needed to be applied, tested, extended, and exploited. The practical rewards were enormous, but the foundational questions never disappeared. They just waited, patiently, for someone to take them seriously again. Meanwhile, de Broglie's prediction about matter waves was put to the test, and in 1927, it was experimentally confirmed when Clinton Davison and Lester Germer at Bell Labs in New York fired electrons at a nickel crystal and observed a diffraction pattern. The electrons scattered off the crystal exactly the way X-rays scatter off crystal planes. The electrons were behaving as waves, and here is the delicious irony that people love to point out. J. Thomson, the father, won the Nobel Prize for discovering the electron as a particle. His son, George Paget Thomson, won the Nobel Prize for showing that the electron is a wave. Father proves it is a particle. Son proves it is a wave. Both were right. Let me dwell on de Broglie's insight a little longer, because there is a subtlety that is easy to miss, and it connects to something much deeper. When de Broglie proposed that matter has wave-like properties, with a wavelength equal to Planck's constant divided by momentum,
he was doing something more radical than it might appear. He was not just saying that electrons wiggle. He was proposing a universal relationship between two seemingly unrelated descriptions of the world: the particle description, defined by momentum, and the wave description, defined by wavelength. And the bridge between them was Planck's constant. This relationship had already been known for photons. Einstein had shown that a photon's energy is h times its frequency, and since the energy and momentum of a photon are related by special relativity, the momentum is h divided by the wavelength. De Broglie simply asked, what if this relationship applies to everything? Not just photons, not just light, everything. Electrons, protons, baseballs, people. Everything that has momentum has a wavelength, and the wavelength is h over the momentum. For large objects, the wavelength is absurdly small. A baseball thrown at about 90 miles per hour weighs around 5 ounces. When you calculate its momentum and divide Planck's constant by that number, you get a wavelength of about 10 to the minus 34 meters, a decimal point followed by 33 zeros and then a digit. That is not just small, that is smaller than anything meaningful in physics. It is smaller than the Planck length, the scale at which our current understanding of space itself breaks down. There is no conceivable way to observe the wave nature of a baseball. The wavelength is so tiny that the wave crests are packed impossibly close together, far beyond the reach of any measurement. But for an electron with a typical energy in an atom has a wavelength on the order of a few tenths of a nanometer. That is comparable to the size of the atom itself. And when the wavelength of a particle is comparable to the size of the system it is in, wave effects dominate. The electron cannot be thought of as a tiny ball orbiting a nucleus. It fills the atom. It wraps around the nucleus like a standing wave, and only certain wavelengths fit, which is why only certain energies are allowed. This is a beautiful unification. The quantization that Bohr had imposed by fiat, the rule that angular momentum comes in integer multiples of h bar, turns out to be a natural consequence of the wave nature of the electron. You do not need to decree it. It falls out of the physics. Standing waves have nodes and antinodes, and only whole numbers of wavelengths fit around a closed orbit, and that automatically constrains the angular momentum. The quantum is not a postulate. It is a consequence of the wave nature of matter. De Broglie's thesis committee was reportedly uncertain about what to make of this idea. The mathematician Paul Langevin, who was the thesis advisor, sent a copy to Einstein, asking for his opinion. Einstein's response was enthusiastic. He said that de Broglie had lifted a corner of a great veil. The thesis was accepted, and de Broglie received his doctorate. 5 years later, he won the Nobel Prize. And now, let me go deeper into the path integral, because Feynman's reformulation is where the full strangeness really comes together. Feynman developed his approach in the late 1940s, while he was a young professor at Cornell. He had been a student of John Archibald Wheeler at Princeton, and he was already known as a brilliantly unconventional thinker. The kind of person who would rederive results from scratch rather than look them up, partly because he enjoyed the process, and partly because he distrusted any understanding that was not his own. The standard way of doing quantum mechanics at the time was the Schrödinger equation. You write down the equation, apply boundary conditions, solve for the wave function, extract probabilities. It is powerful and general, but it is also, in a sense, indirect. You are solving a differential equation to get a function, and then interpreting the function probabilistically. The path integral bypasses all of this. It goes directly from the question, what is the probability that a particle starting at point A ends up at point B, to the answer, by adding up contributions from all possible paths connecting A and B. And the prescription is shockingly simple.
Every path from A to B gets an amplitude. The amplitude is a complex number. It has a magnitude and a phase. The magnitude is the same for every path. They all have equal weight. What differs is the phase,
and the phase is determined by the action of the path divided by h bar. The action, as I mentioned earlier, is the integral of kinetic energy minus potential energy over time. In classical mechanics, the path a particle actually takes is the one that minimizes, or more precisely makes stationary, the action. This is the principle of least action, discovered by Euler and Lagrange in the 18th century and refined by Hamilton in the 19th. It is a beautiful and powerful principle, but in classical mechanics, it seems like just an elegant mathematical trick. You can derive Newton's laws from it, but Newton's laws are more intuitive, and most physicists treat the principle of least action as a shortcut rather than a fundamental law.
Feynman's path integral tells you that the principle of least action is not a shortcut. It is the whole story. But it is the whole story in a quantum context, where every path contributes, not just the classical one. The classical path is special only because paths near it happen to have similar phases, and therefore add up constructively. Far from the classical path, the phases are wildly different, and the contributions cancel. There is a number that determines how spread out the contribution of different paths is, and that number is h bar, Planck's constant. For macroscopic objects, with actions enormously larger than h bar, only an infinitesimally narrow bundle of paths around the classical trajectory contributes. The quantum fuzz is invisible. For microscopic objects, with actions comparable to h bar, many paths contribute, and the quantum nature of reality becomes apparent.
So Planck's constant, that tiny number introduced in 1900 to solve the blackbody problem, turns out to be the parameter that controls the transition from quantum to classical. It is the size of the grain in the fabric of reality. When your action is much larger than one grain, the world looks smooth and classical. When your action is comparable to one grain, the graininess shows through, and you see quantum effects. And the action, this abstract quantity that combines kinetic energy, potential energy, and time, turns out to be the most fundamental quantity in all of physics. Not force, not energy, not momentum. Action. Feynman's formulation makes this explicit, but it was there all along, hiding in the mathematics of quantum mechanics from the very beginning. Planck's constant has units of action. The uncertainty principle constrains products of quantities that together have units of action.
The Schrödinger equation is, at its core, about the evolution of phases driven by the action. As the theoretical physicist in the Veritasium video put it, nobody in particle physics approaches their field from any viewpoint other than least action. When physicists search for new laws of nature, what they are really searching for is the right Lagrangian, the function that, when integrated over time, gives the correct action, the correct rules for how phases evolve, the correct sum over paths. The hunt for a theory of everything is, at its deepest level, a hunt for the Lagrangian that generates all the laws of physics. The principle of least action was almost a footnote in classical mechanics, a cute mathematical trick. But Feynman's path integral reveals it as the quantum mechanical origin of classical mechanics. And that is, I think, one of the most beautiful revelations in the history of science. The everyday world of definite trajectories and predictable motions is not fundamental. It is an emergent phenomenon, arising from the constructive interference of innumerable quantum paths, the vast majority of which cancel out, leaving only the classical path visible. Now, with all of that as background, with the understanding that particles are also waves, that waves are also particles, and that these two descriptions are somehow both true, we can finally approach the experiment that takes this strangeness to its absolute limit. The double-slit experiment. In its simplest form, you fire particles, photons or electrons, or even whole atoms, at a barrier with two narrow slits cut in it. Behind the barrier is a screen that records where each particle lands. You fire the particles one at a time, so there is no possibility of them interacting with each other. If particles were just particles, little bullets, You would expect them to go through one slit or the other and pile up in two bands behind the two slits, the way sand would pile up if you threw it through two gaps in a fence. But that is not what happens. Over time, as thousands of individual particles hit the screen one by one, a pattern emerges. An interference pattern. Bright bands alternating with dark bands, exactly the kind of pattern you get when two waves overlap and their crests and troughs reinforce or cancel each other. Each individual particle lands at a definite point on the screen, like a bullet. But the overall pattern, built up from thousands of individual hits, is a wave pattern. Each particle somehow interfered with itself. And here is the truly disturbing part. If you try to figure out which slit each particle went through, if you put a detector at the slits to observe which one the particle chose, the interference pattern disappears. You get the two-band pattern you would expect from bullets. The act of observing which slit the particle goes through changes the outcome of the experiment. When you do not look, the particle behaves like a wave, going through both slits simultaneously, interfering with itself, producing the wave pattern. When you do look, it behaves like a particle, going through one slit, producing the bullet pattern. What you choose to measure determines what reality looks like. We will come back to the philosophical implications of that in a later chapter. For now, I want to follow a different thread, because the double-slit experiment leads somewhere even more radical, somewhere that took until the 1940s to fully appreciate. There is a story, and the story may or may not be literally true, but the logic in it is flawless. The story goes like this. A professor is teaching the double-slit experiment. He explains the setup. Electrons are fired one at a time through two slits to a screen.
Because you cannot determine which slit each electron went through, quantum mechanics says each electron goes through both slits simultaneously. To find the probability of the electron landing at a particular point on the screen, you add up the amplitude of the wave going through one slit with the amplitude going through the other slit, and you square the result. A student raises his hand. What if there are 3 slits? Well, says the professor, you add up the amplitudes from all 3 slits and square the result. Same principle. What about 4 slits? 5? The professor is getting impatient. The answer is the same for any number of slits. You just add up the amplitudes from all of them. And then the student asks the question that changes everything. What about infinite slits? What if the barrier has infinitely many slits, so that it effectively disappears? And what if you then add a second barrier behind it, also with infinitely many slits? And a third? And a fourth?
The student's point is devastating. If the math of the double-slit experiment says you have to consider all the paths the particle might take through the slits, and if removing the barrier entirely is just the limiting case of infinitely many slits, then even when there are no barriers at all, even when a particle is just traveling through empty space from one point to another, you have to consider all possible paths it could take to get there. According to the story, that student was Richard Feynman. The story is almost certainly invented, but the logic is perfect, and the logic leads to something extraordinary. In the 1940s, Feynman developed a complete reformulation of quantum mechanics based on this idea. It is called the path integral formulation, or sometimes the sum over histories. And it says that when anything, a photon, an electron, a proton, anything, moves from one point to another, it does not take a single path. It takes every possible path simultaneously.
Every conceivable route from here to there, including routes that zigzag, routes that loop around, routes that go backward in time, routes that go to the far side of the galaxy and back. This sounds completely insane, but the math makes it precise. Each path is assigned a weight, and that weight is determined by a single quantity, the action of the path. The action, as we touched on when discussing Planck, is the integral of kinetic energy minus potential energy over time. Every path has an action value, and from that action, you calculate the phase, the direction of a tiny arrow, a complex number. As the particle follows a given path, the phase accumulates, spinning around like a clock hand. The crucial detail is how fast the phase spins. It is determined by the action divided by Planck's constant, h bar. And h bar is unimaginably small. For everyday objects like a thrown baseball, the action along any path is enormous compared to h bar. Enormous. We are talking about numbers like 10 to the 32nd. So the phase spins around billions of billions of billions of times along any given path. And for a slightly different path, the action might be slightly different, say by 100th of a joule second, which sounds like almost nothing. But when you divide by h bar, the phase spins an additional 10 to the 32 times. The arrow ends up pointing in a completely random direction. This means that for any two nearby paths, the arrows point in random, uncorrelated directions. When you add them up, they cancel. They destructively interfere. Almost all possible paths contribute nothing to the final result, because their phases are wildly different from their neighbors, and they all wash out. Almost all. There is one special set of paths where this does not happen. The paths closest to the path of least action. At the minimum of a curve, small changes to the input produce no change in the output to first order. The action is stationary. So paths near the path of least action have nearly the same phase. Their arrows point in nearly the same direction. They add up. They constructively interfere. And that is why a baseball follows a parabola. Not because the baseball knows calculus, not because some force is pushing it along that precise curve, but because the baseball, like everything else, is simultaneously exploring every conceivable path from your hand to the ground. And the overwhelming majority of those paths, the ones that go to the moon, the ones that zigzag through the stratosphere, the ones that go backward in time, cancel each other out. The only paths that survive, the only ones whose contributions add up rather than washing out, are the ones clustered around the classical trajectory, the path of least action. Classical mechanics is not a separate theory. It is a consequence of quantum mechanics in the limit where the action is much larger than Planck's constant.
Your everyday experience of objects following definite trajectories is, in a very precise sense, a constructive interference effect. It is the illusion that emerges when the quantum contributions from trillions of alternative paths cancel out, leaving only the classical path visible. For an electron inside an atom, the situation is completely different. The action is comparable to h bar. The paths near the classical trajectory do not dominate overwhelmingly. Many paths contribute. The electron is genuinely spread out, genuinely fuzzy, genuinely exploring multiple routes simultaneously. This is why electrons in atoms do not have orbits. They have orbitals, probability clouds, because the wave nature of the electron at these scales cannot be hidden by cancellation. And here is the beautiful part. There is an experiment that demonstrates, viscerally and unmistakably, that light really does explore all possible paths, including the impossible ones that should not contribute. Consider a mirror. When you shine a light at a mirror, it reflects at a specific spot. The angle of incidence equals the angle of reflection. That is where the light should go, according to classical optics. But according to Feynman's path integral, light also goes everywhere else on the mirror. It reflects from the edges, from the corners, from every point on the surface. The reason you do not see reflections from those other points is that the phases from nearby paths at those locations spin rapidly and cancel out.
The arrows from neighboring paths point in all directions and add up to nothing. But, and this is the clever part, what if you could selectively block some of those cancelling paths? If you covered the surface of the mirror with very fine alternating stripes, blocking every other group of paths, then the paths that remain no longer fully cancel. Their arrows no longer average to zero.
They add up, and you see a reflection from a place where classically there should be no reflection at all. This is exactly what a diffraction grating does, and the demonstration works. A physicist named Caspar, working with the team that produced the Veritasium video on this topic, showed it live. He took a laser, pointed it at a spot on a mirror where no reflection should be visible, and confirmed that indeed no light appeared. Then he placed a piece of foil with about 25,000 lines per inch on that same spot, and the light appeared, reflected from a place where, classically, it has no business being. The foil did not add any light, it blocked some. And by blocking the right pattern of paths, it removed the cancellation that had been hiding the light that was always, secretly, going there. He described it as the coolest demo he had ever done, and I think he might be right, because it is not just a trick, it is a window into the actual mechanism of reality. Light genuinely does explore every possible path, from source to destination. The classical law of reflection, angle of incidence equals angle of reflection, is not a fundamental rule. It is a statistical consequence of constructive interference among the paths near the path of least action. Remove the cancellation, and the hidden paths reveal themselves. Everything, light, electrons, protons, baseballs, planets, does this. Everything takes every possible path. The difference between the quantum world and the classical world is not a difference in kind. It is a difference in scale. When the action is tiny, the paths fan out, and the quantum nature of reality is visible. When the action is huge, the cancellation is so complete that only one path survives, and the world looks classical. And this is where the deeper story of quantum mechanics really begins. Because everything we have discussed so far, the quantization of energy, the particle nature of light, the wave nature of matter, the path integral, all of this is, in a sense, mechanics. It is about how things move and what their energies are. What it does not yet address is the really disturbing question: what happens when you measure something? What happens when you look? Because Feynman's path integral tells you to add up all the paths. The double slit experiment tells you the electron goes through both slits. But when you put a detector at one of the slits, the electron goes through only one. The act of measurement collapses the superposition, and nobody, in 1927 or in 2026, can fully explain how or why that happens. The next experiment takes us straight into that mystery. The experiment that proved properties don't exist until measured. Everything we have talked about so far has been strange, but there is a way to convince yourself it is not that strange. You can tell yourself a story. You can say, okay, energy comes in chunks, fine. That is just a rule about how atoms emit and absorb. Light comes in particles, fine. Photons are just little packets of wave energy. Electrons have wavelengths, fine. They are just very small and fast and wave-like. The double slit produces interference patterns, fine. The electron just goes through both slits at the same time, the way a water wave would. It is weird, but you can still picture it as something going through space, something with definite properties, something that is just behaving in an unusual way. The experiment we are about to discuss makes that comforting story impossible. In 1922, two German physicists named Otto Stern and Walter Gerlach performed an experiment that, on the surface, seems straightforward.
They took a beam of silver atoms and sent it through an inhomogeneous magnetic field, a magnetic field that was stronger on one side than the other. The atoms, which behave like tiny magnets because of the motion of their electrons, should be deflected by this uneven field. Atoms whose magnetic orientation is aligned with the field should be pushed one way, and atoms oriented the other way should be pushed the opposite way. In classical physics, you would expect the atoms to arrive at the detector smeared out in a continuous band. After all, the atoms in the beam should have their magnetic orientations pointing in all possible directions, some up, some down, some tilted at various angles. A continuous range of orientations should produce a continuous range of deflections. What Stern and Gerlach saw was not a continuous band.
It was two distinct spots, two and only two. Every single atom was deflected either all the way up or all the way down. Nothing in between. No atoms arrived at intermediate positions. It was as if every atom, upon entering the magnetic field, had to choose up or down. There were no other options. This was the discovery of quantized angular momentum, what physicists now call spin. And it is one of the most important and most deeply puzzling results in quantum mechanics. Now, spin is a misleading word. It suggests that the electron is literally spinning, rotating around an axis, the way the Earth spins on its axis. Early physicists used that analogy, and the name stuck. But electrons are not actually spinning. They are not rotating in the classical sense. Spin is a purely quantum mechanical property that has no classical counterpart.
It is something that particles just have, the way they have mass and charge. Except that unlike mass and charge, spin does not correspond to any motion or structure. There is nothing inside the electron going around in circles. Spin is intrinsic. It is just there. For an electron, the spin comes in only two possible values when you measure it along any direction. You can call them spin up and spin down, or clockwise and counterclockwise, or plus 1/2 and minus 1/2. The specific labels do not matter. What matters is that there are exactly two possibilities and nothing in between. And here is where things get genuinely strange. Let me walk through this carefully, because this is the heart of the matter. Suppose you set up a Stern-Gerlach apparatus oriented vertically, measuring the spin of an electron in the up-down direction. You send an electron through. It comes out either spin up or spin down, with equal probability, 50-50. Fine. Now suppose the electron comes out spin up. You know its vertical spin. It is up. Now take that same electron and send it through a second Stern-Gerlach apparatus, but this time oriented horizontally, measuring the spin in the left-right direction. What happens? The electron comes out either spin left or spin right, again with 50-50 probability. Okay, now you know its horizontal spin too. Or do you? Here is the test. Take that electron, which you just measured to be spin right in the horizontal direction, and send it through a third apparatus, oriented vertically again, measuring the up-down spin once more. If the electron still remembers that it was spin up from the first measurement, it should come out spin up. After all, you measured it, you found it was up. That fact should still be true. But it does not come out spin up. It comes out spin up or spin down with 50-50 probability, as if the first measurement had never happened. Think about what this means. By measuring the horizontal spin, you destroyed the information about the vertical spin. The electron does not have a definite vertical spin and a definite horizontal spin at the same time. Measuring one erases the other. And this is not a limitation of your measuring apparatus.
It is not that the measurement is somehow disturbing the electron and scrambling the information. It is more fundamental than that. The electron literally does not possess both properties simultaneously. The vertical spin and the horizontal spin cannot coexist as definite values. This is the essence of the Heisenberg uncertainty principle, which the young German physicist Werner Heisenberg formulated in 1927. The uncertainty principle is often described in terms of position and momentum. You cannot know both the exact position and the exact momentum of a particle at the same time. But its deepest form is about what physicists call incompatible observables. Certain pairs of properties are fundamentally incompatible. Knowing one precisely means the other is completely undefined. Not unknown, undefined. The property does not have a value. To see why this happens mathematically, you need the concept of operators, which is one of the three key ideas in the mathematical formalism of quantum mechanics. An operator is a mathematical instruction that acts on the wave function, the mathematical object that describes the state of the system. The position operator, for instance, tells you something about where the particle might be found. The momentum operator tells you something about how fast it is moving. And the spin operators tell you about the spin along different directions. Now, with ordinary numbers, the order of multiplication does not matter. 3 times 5 is the same as 5 times 3. But operators are not ordinary numbers. They are mathematical operations, and the order in which you apply them can make a difference. If you apply the position operator first and then the momentum operator, you get a different result than if you apply them in the reverse order. Mathematicians say the operators do not commute. Remember Heisenberg on that windswept island in the North Sea, working through the nights on his matrices. The discovery that disturbed him so much he could not sleep, the discovery that A times B does not equal B times A, turns out to be exactly this. The matrices he constructed were operators, and the fact that multiplying them in different orders gives different results is the mathematical root of the uncertainty principle. Position and momentum do not commute. Spin along the vertical axis and spin along the horizontal axis do not commute. And when two operators do not commute, the properties they represent cannot both have definite values at the same time.
This is worth pausing on, because it connects the abstract mathematics to the physical strangeness we just witnessed in the Stern-Gerlach experiment. The reason measuring the horizontal spin erases the vertical spin is not that the measurement apparatus is clumsy. It is that the operators for horizontal spin and vertical spin do not commute. The mathematical structure of quantum mechanics forbids these two properties from coexisting as definite values. The universe enforces this prohibition absolutely, regardless of how clever your experiment is. And this connects to the deeper puzzle that Born's probabilistic interpretation left open. If the wave function gives you only probabilities, if it tells you the odds of finding the electron here or there, spin up or spin down, then what is happening between measurements? What is the electron doing when nobody is looking? The Schrödinger equation, which governs how the wave function evolves over time, is perfectly deterministic.
Given the wave function at one moment, it tells you exactly what the wave function will be at any later moment. There is no randomness in the equation. The wave function spreads out, interferes, oscillates, entangles, but it does so smoothly and predictably. The randomness enters only at the moment of measurement. Only when you ask the wave function a question. Where is the particle? What is its spin? Do you get a random answer, weighted by the probabilities encoded in the wave function. And after the measurement, the wave function changes abruptly. It snaps to the state corresponding to the result you obtained, discarding all the other possibilities. This sudden change is called the collapse of the wave function. And the
The question that has haunted quantum mechanics for a century is, what causes it? What makes the wave function collapse? When exactly does it happen? How does a smooth, deterministic evolution governed by the Schrödinger equation suddenly produce a sharp, random, irreversible jump? The Schrödinger equation itself contains no such jump. The collapse is something extra, a separate rule layered on top, a rule that says, when a measurement happens, stop using the Schrödinger equation and apply a different procedure, the one that gives you probabilities and a definite outcome. Erwin Schrödinger himself was so disturbed by this situation that in 1935 he came up with a thought experiment designed to highlight just how absurd it seemed. This is the famous thought experiment with the cat. Imagine a box containing a radioactive atom, a Geiger counter, a vial of poison, and a cat. The radioactive atom has a 50-50 chance of decaying within 1 hour. If it decays, the Geiger counter detects the radiation and triggers a mechanism that breaks the vial of poison, killing the cat. If it does not decay, the cat lives. Now, according to quantum mechanics, until someone opens the box and looks, the radioactive atom is in a superposition of decayed and not decayed. And if the atom is in a superposition, then the Geiger counter is in a superposition of triggered and not triggered. And the vial is in a superposition of broken and intact. And the cat is in a superposition of alive and dead. Schrödinger did not propose this thought experiment because he believed the cat was really in a superposition. He proposed it because he thought the conclusion was absurd, and he wanted to show that something was wrong with the quantum mechanical description of measurement. Cats are obviously either alive or dead, they are not both. So somewhere between the microscopic quantum world and the macroscopic world of cats, the superposition has to break down. But where? And how? Nobody has a universally accepted answer to that question, not in 1935 and not in 2026.
Different interpretations of quantum mechanics give different answers, and we will come to those in the final chapter. But the experimental facts are clear, and they have been confirmed thousands of times. At the microscopic level, properties genuinely do not have definite values until they are measured. The electron does not have a position until you detect it. The spin does not have a direction until you check. Measurement does not reveal pre-existing facts about the system, it creates them. This is, I think, the single most difficult thing about quantum mechanics for most people to accept. Not the math, not the probabilities, not the wave-particle duality. Those are strange, but they are abstractly strange. The measurement problem is intimately strange. It says that the world you observe is not the world that exists independently of your observation. It says that the act of looking, at the deepest level physics has been able to probe, is not passive.
It participates in creating what is seen. Einstein, when confronted with this idea, was deeply unhappy. He once asked a colleague, reportedly Abraham Pais, whether Pais really believed the moon was not there when nobody looked at it. The question sounds almost silly, but it gets at the heart of the matter. In classical physics, the moon is there whether you look or not. Its properties, its position, its momentum, its mass, exist independently of any observer. Quantum mechanics, at least in its standard formulation, denies this for microscopic systems. The electron's position is not there when nobody looks. And Einstein, from the mid-1920s until his death in 1955, never accepted this.
He was convinced that quantum mechanics, as successful as it was at making predictions, was an incomplete theory, that there must be some deeper level of description where particles do have definite properties at all times, and the apparent randomness of quantum measurements reflects our ignorance of those deeper properties, not a genuine indeterminacy in nature. Let me go deeper into the formalism here, because there is a way of thinking about quantum mechanics that makes the measurement problem even more stark. and it comes directly from the mathematical structure that Heisenberg stumbled upon on Heligoland. In classical mechanics, the state of a system is specified by a list of numbers. A particle in three-dimensional space has a position, 3 numbers, and a momentum, 3 more numbers. That is all. 6 numbers completely determine the state of the particle. If you know those 6 numbers, you can use Newton's laws to predict all 6 numbers at any future time.
The state is a point in a 6-dimensional space called phase space, and the laws of physics trace out a definite trajectory through that space. In quantum mechanics, the state of a system is specified by a vector in a much more abstract space called Hilbert space. For a particle with spin, the Hilbert space is infinite dimensional. You need infinitely many numbers to specify the state. But the key difference is not just the size of the space, it is the nature of how you extract information from it. In classical mechanics, you can always ask, what is the position of the particle? And you always get a definite answer. The position is one of the numbers that defines the state. It is just sitting there, waiting to be read off. In quantum mechanics, the state vector does not contain a definite position. It contains amplitudes, complex numbers, for every possible position. When you ask, where is the particle?
You are applying the position operator to the state vector, and what you get back is not a position, but a probability distribution over all possible positions. The state vector tells you the odds of finding the particle here or there, but until you measure here and there are both present in the state, coexisting as components of a superposition. And the same goes for momentum, spin, energy, and every other observable property. Each property is associated with an operator, and the state vector contains information about all of them simultaneously. But here is the catch. You cannot extract all that information at once. Measuring one property, precisely determining one observable, generally disturbs the state in a way that scrambles the information about incompatible observables. This is not because your measuring device is clumsy or your technique is poor. It is because of the mathematical structure of Hilbert space. Operators that do not commute, operators whose order of application matters, correspond to observables that cannot be simultaneously defined. Position and momentum are the most famous pair, but there are many others. The spin along different axes, as we saw with the Stern-Gerlach experiment, is another. Leonard Susskind, in his textbook, The Theoretical Minimum, makes a point about this that I find particularly illuminating. He begins the entire book with spin, not with wave functions, not with the Schrödinger equation, but with spin. And the reason is that spin is the simplest possible quantum system. A single electron spin has only 2 possible measurement outcomes, up or down. The Hilbert space is 2-dimensional. You can write down the state vector completely using just 2 complex numbers. And yet, even in this absurdly simple system, all the essential strangeness of quantum mechanics is already present. Superposition, measurement, collapse, uncertainty, entanglement. All of it shows up in the 2-dimensional Hilbert space of a single spin. This is why physicists often say that a qubit, a quantum bit, the basic unit of quantum information, captures the essence of quantum mechanics. A qubit is just a quantum system with 2 states. But the way those 2 states can be superposed, the way measurement collapses the superposition, the way 2 qubits can be entangled, all of these features generalize directly to more complex systems. If you understand the qubit, you understand the framework. The rest is details. And here is the deepest puzzle. The Schrödinger equation, which governs how the state vector evolves over time, is perfectly deterministic. Given the state at one time, it produces a unique state at any later time. There is no randomness in the equation. There is no collapse. The wave function spreads out, interferes, oscillates, entangles, but it does so smoothly and predictably. The randomness enters only when you measure, only when you ask the state vector a question. What is your position? What is your spin? Do you get a random answer, weighted by the probabilities that the state vector encodes? And after the measurement, the state vector is different from what the Schrödinger equation would have predicted. It has collapsed to the eigenstate corresponding to the measured value, discarding all the other possibilities. There are two rules in quantum mechanics, and they contradict each other. Rule 1. The state evolves deterministically according to the Schrödinger equation. Rule 2. When a measurement is made, the state collapses randomly to one of the possible outcomes. Rule 1 is elegant, unified, continuous, and deterministic. Rule 2 is messy, ad hoc, discontinuous, and probabilistic. And nobody has a completely satisfying explanation for why there need to be two rules instead of one. This is the measurement problem. And it is worth emphasizing, it is not a philosophical curiosity. It is a gap in the logical structure of the theory. The theory gives you two mutually exclusive rules of evolution, does not tell you when to apply which one, and does not define what constitutes a measurement. Any attempt to define measurement in physical terms as an interaction between a quantum system and a macroscopic apparatus immediately runs into the problem that the apparatus itself is made of atoms, and atoms obey quantum mechanics. So you can, in principle, describe the apparatus using a wave function and apply the Schrödinger equation to the whole system, apparatus and all. And when you do, you get a larger superposition, no collapse. The measurement problem is not solved by adding more quantum mechanics. It is a problem about quantum mechanics.
This is what led Schrödinger to his famous cat thought experiment. He was not being playful. He was being deadly serious. He was pointing out that if you take quantum mechanics at face value and apply it to macroscopic objects, you get predictions that are absurd. A cat in a superposition of alive and dead. And therefore something must be wrong or incomplete about the way we interpret the theory. The question is what? And different answers to that question lead to radically different pictures of reality. But before we get to those pictures, there is one more experimental result that deepened the mystery even further. Because up to this point, you might hope that the strangeness of quantum mechanics is confined to single particles, that when you have two or more particles, things might somehow average out and become more sensible. Einstein certainly hoped for something like that.
And in 1935, he constructed an argument designed to show that quantum mechanics, applied to two particles, leads to a conclusion so absurd that the theory must be incomplete. He was wrong about the conclusion. But the phenomenon he identified, quantum entanglement, turned out to be even stranger than he imagined. This conviction led him, in 1935, to construct the most famous argument against the completeness of quantum mechanics. An argument that used a phenomenon so strange, so counterintuitive, that Einstein himself called it spooky. And that phenomenon is entanglement. There is one more experiment that I want to mention before we leave this chapter, because it takes the strangeness of quantum measurement to what might be its absolute limit, and it connects directly to the question of whether the future can influence the past.
It is called the delayed choice quantum eraser, and it was first proposed by the physicist Marlon Scully in the early 1980s and experimentally realized in various forms over the following decades. The setup is a variation on the double slit experiment. You fire photons at two slits, and behind the slits you use a special crystal to convert each photon into a pair of entangled photons. One photon from each pair, call it the signal photon, goes to a screen where its position is recorded. The other photon, call it the idler photon, goes through a series of beam splitters and detectors that either preserve or erase the information about which slit the original photon went through. Here is the remarkable result. When you look at all the signal photons together,
regardless of what happened to their idler partners, you see no interference pattern, just a smooth, featureless distribution. The which path information exists in the idler photons, and its existence is enough to destroy the interference, even though nobody has looked at it yet. But when you sort the signal photons into two groups, those whose idler partners were detected in a way that erased the which path information, and those whose idler partners were detected in a way that preserved it, you find that the first group shows an interference pattern, and the second group does not. The two patterns add up to the featureless distribution you see when you look at all the signal photons together, but when separated, each group tells a different story. And here is the truly mind-bending part. The signal photon hits the screen before the idler photon reaches its detector. The decision about whether to erase or preserve the which path information is made after the signal photon has already been recorded. The signal photon has already landed on the screen, at a definite position, before the idler photon's fate is decided. Yet when you sort the data later, based on what happened to the idler photons, you find that the signal photons knew, in some sense that is very difficult to articulate precisely, whether their which path information would be erased or preserved. The ones whose idler partners would later be erased show interference. The ones whose idler partners would later be preserved do not. Does this mean the future influences the past? Physicists are very careful about this. The consensus is that no, it does not, because you cannot see the pattern in the signal photons until you sort them using the idler photon data, and that sorting requires information that travels at the speed of light or slower. You cannot use the delayed choice eraser to send messages backward in time or to predict the future.
The interference pattern is hidden until you have both pieces of the puzzle, the signal photon's position and the idler photon's detection, and combining those pieces requires classical communication. But the experiment still leaves you with a deep sense of unease. The correlations are real. The sorting reveals a genuine pattern that was invisible before, and the timing suggests that something very strange is happening to the ordinary notion of cause and effect at the quantum level. John Archibald Wheeler, who was Feynman's PhD advisor and one of the great visionaries of 20th century physics, proposed an even more dramatic version of this idea in the 1970s. He called it the delayed choice experiment. In Wheeler's version, you set up a double slit-like apparatus for photons and delay the decision about whether to observe which path the photon took until after the photon has already passed through the slits. You decide after the fact whether to test for particle behavior or wave behavior, and the photon, which has already traveled through the apparatus, seems to retroactively adjust its behavior based on your later decision. Wheeler loved this kind of thinking. He was fond of saying that quantum mechanics shows us that the past has no existence except as it is recorded in the present. The history of a quantum event is not fixed until the measurement is complete. In a sense, the measurement reaches back in time and gives the event its character. Whether you take this literally or as a provocative way of describing the mathematics depends on your interpretation of quantum mechanics. In the Copenhagen view, it simply means that you should not talk about what happened before the measurement. In the many worlds view, all outcomes occur, and the delayed choice just determines which branch you find yourself in. In the pilot wave theory, the particle always had a definite path, guided by the pilot wave, and there is no mystery about the past. But regardless of interpretation, the delayed choice experiments have been performed, and they confirm the quantum predictions. Whatever is going on, the ordinary notion that the past is fixed and the future is open does not apply straightforwardly in the quantum world. This, I think, is a fitting place to pause, because we have now touched all the major sources of confusion in quantum mechanics. Energy is quantized. Light is both wave and particle. Particles explore all possible paths. Properties do not exist until measured. The act of measurement is mysterious and possibly reaches backward in time. Entangled particles are correlated in ways that defy local explanation, and the meaning of the theory is still in dispute. Every one of these statements is supported by experiment. Every one of them has been confirmed to extraordinary precision.
And every one of them violates our everyday intuitions about how the world should work.
There is a quote from Shakespeare that one physics lecturer uses to set the right attitude for approaching quantum mechanics, and I think it is perfect for this moment. In Hamlet, Horatio says, "O day and night, but this is wondrous strange." And Hamlet replies, "And therefore, as a stranger, give it welcome." There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. Quantum mechanics is wondrous strange, and the appropriate response is not to resist it or to demand that it make intuitive sense, but to welcome it as a stranger. To approach it with an open mind, to let the strangeness wash over you, and to appreciate the extraordinary fact that human beings, using nothing but their minds and their experiments, managed to discover these truths about the deepest level of reality. The physicists who built quantum mechanics were not comfortable with it either. Planck tried to undo his own discovery. Einstein never accepted it. Schrödinger regretted his equation. Bohr tied himself in philosophical knots trying to interpret it. Heisenberg was so unsettled by his own results that he could not sleep. And Feynman, who understood it as well as anyone who ever lived, famously said that nobody understands quantum mechanics. But they pushed through their discomfort because the experiments demanded it. Nature told them what the rules were, and they listened, even when the rules were strange beyond imagining. And what they found on the other side of that strangeness was the most powerful and precise description of reality that human beings have ever constructed. The experiment that proved the universe is non-local. The year is 1935. Albert Einstein is 56 years old, living in Princeton, New Jersey, permanently exiled from Europe by the rise of the Nazis. He has been in a running intellectual battle with Niels Bohr and the Copenhagen School for nearly a decade, arguing that quantum mechanics, while experimentally successful, cannot be a complete description of reality. His objections are not woolly or philosophical. They are precise, technical, and carefully constructed. At the Solvay conferences of 1927 and 1930, Einstein had presented a series of thought experiments designed to show that the uncertainty principle could be circumvented, that you could, in principle, measure both the position and momentum of a particle simultaneously, contradicting Heisenberg. Each time, Bohr had found a flaw in Einstein's argument. Each time, the uncertainty principle survived. In one famous exchange, Bohr actually used Einstein's own general relativity against him, pointing out that the gravitational redshift of a photon escaping a box introduced exactly the uncertainty Einstein had tried to eliminate.
Einstein conceded the point, but remained unconvinced. And in 1935, he found a new angle of attack, one that did not try to violate the uncertainty principle directly, but instead used quantum mechanics' own rules to derive a conclusion so bizarre that it seemed to prove the theory must be incomplete. The argument was published in a paper by Einstein, Boris Podolsky, and Nathan Rosen, universally known as the EPR paper, after the initials of the three authors. It is one of the most important papers in the history of physics, and its consequences are still being worked out today. Here is the idea, simplified to its essence. Suppose you have two particles that have interacted at some point and then separated. Quantum mechanics says that these two particles can be in what is called an entangled state, a state in which the properties of the two particles are correlated in a very specific way, even after they have moved far apart. To make this concrete, think about spin, the property we discussed in the last chapter.
Suppose you create a pair of particles whose total spin is 0. One is spin up and the other is spin down, but, and this is the crucial point, until you measure them, neither particle has a definite spin. They are in a superposition. What quantum mechanics says is that the combined state is a superposition of particle A is up and particle B is down, with particle A is down and particle B is up. The pair has a definite total spin of 0, but the individual particles do not have definite spins. Now separate the particles. Send one to London and the other to Tokyo. Wait until they are thousands of miles apart. Then measure the spin of the particle in London. Suppose you find it is spin up. At that instant, you know with absolute certainty that the particle in Tokyo is spin down. You do not need to measure it. You know. The correlation is perfect.
Einstein's argument was this. At the moment you measure the London particle, the Tokyo particle is thousands of miles away. No signal, no light, no influence of any kind can travel from London to Tokyo instantaneously. That would violate the speed of light. So whatever the Tokyo particle does when you measure the London one, it must not involve any actual physical influence traveling between them. The Tokyo particle must have already had a definite spin before you measured the London one. The measurement in London merely revealed a pre-existing fact about the Tokyo particle. It did not create that fact. And if the Tokyo particle already had a definite spin before measurement, then quantum mechanics, which says the spin is undefined until measured, must be an incomplete description of reality. There must be additional information, what physicists later called hidden variables, that determines the outcome in advance.
Quantum mechanics, with its probabilities and superpositions, is just averaging over these hidden variables that we have not yet figured out how to access. This is a beautiful argument. It is logically rigorous. It rests on two seemingly unassailable assumptions. The first is locality. A measurement here cannot instantaneously affect a particle there. No faster than light influences. The second is realism. If you can predict the value of a physical quantity with certainty without disturbing the system, then that quantity must have a definite value, an element of physical reality that exists independently of measurement. Locality and realism. These seem like the most reasonable assumptions in the world. Of course, a measurement here does not affect a particle over there. Of course, things have definite properties when nobody is looking. These are not exotic philosophical positions, they are common sense. Bohr's response to the EPR paper was lengthy and, frankly, difficult to follow.
He argued that you cannot meaningfully talk about the properties of one particle independently of the measurement you perform on the other, because the two particles are part of one entangled system. But he did not directly challenge locality or realism. He shifted the ground of the debate in a way that many physicists found unsatisfying. The general consensus, to the extent there was one, was that EPR had raised an interesting philosophical point, but that the practical success of quantum mechanics rendered it somewhat academic. And there the matter sat, in a kind of philosophical limbo for nearly 30 years. Then, in 1964, a quiet, unassuming physicist named John Stuart Bell, working at CERN in Geneva, did something remarkable. He took Einstein's argument, which had been treated as a purely philosophical question, and turned it into an experimental one. Bell asked, suppose Einstein is right.
Suppose there really are hidden variables that determine the outcomes of quantum measurements in advance. Suppose the correlations between entangled particles are explained by shared information that the particles carried with them when they separated, like identical instructions sealed in two envelopes. What constraints would that put on the statistical correlations you could observe? And Bell proved a theorem. He showed that any theory based on local hidden variables, any theory that satisfies Einstein's assumptions of locality and realism, must obey a specific mathematical inequality. The correlations between measurements on entangled particles cannot exceed a certain limit. If you measure the spins of many pairs of entangled particles along different directions and compile the statistics, the numbers must fall within a certain range, no matter what the hidden variables are, no matter how clever the instruction set is. And then he showed that quantum mechanics predicts correlations that violate this inequality. Quantum mechanics predicts stronger correlations than any local hidden variable theory can produce. This was stunning. It meant that Einstein's assumptions, locality and realism, those seemingly unassailable pillars of common sense, could not both be true if quantum mechanics is correct. At least one of them has to go. But Bell's theorem was a theoretical result. It said, if you do this experiment and get these statistics, then local hidden variables are ruled out. The actual experiment had not been done. That took another 2 decades. The first rigorous test was performed by Alain Aspect and his team in Paris in 1982. They created pairs of entangled photons and measured their polarizations along different directions, separated by enough distance that no signal traveling at the speed of light could get from one measurement to the other in time. They had to close what physicists call the locality loophole, the possibility that the particles could somehow communicate during the measurement. The results were unambiguous. The correlations violated Bell's inequality. They matched the quantum mechanical predictions exactly. Local hidden variables were ruled out. Since then, the experiment has been repeated many times, with increasingly stringent controls, closing one loophole after another. In 2015, 3 independent groups performed what are called loophole-free Bell tests, simultaneously closing both the locality loophole and the detection loophole. The results were the same every time. Bell's inequality is violated. Nature does not obey the constraints of local realism. Let me try to make this more visceral, because the abstract statement, Bell's inequality is violated, does not really convey how strange this is. Imagine a machine that produces pairs of coins. You and a friend each take one coin from a pair and walk to opposite sides of a city. You each flip your coin. For any single flip, the result looks completely random, heads or tails, about 50-50. Nothing strange there. But when you compare results afterward, you find a pattern. Every single time, your coins agree. If yours is heads, your friend's is heads. If yours is tails, your friend's is tails. Perfect correlation, every time, no exceptions. Well, you might think, they are special coins. Maybe the machine just makes matched pairs. Both coins are programmed to come up heads, or both are programmed to come up tails. The programming is random, but it is the same for both coins in the pair. That would explain the correlations without anything spooky. And this is exactly Einstein's position. The correlations are explained by shared information, hidden variables, that the particles carry with them. But Bell showed that this explanation has limits.
If the coins are truly pre-programmed, if the outcome is determined in advance by some hidden instruction set, then when you start flipping the coins at different angles, not just flip normally, but tilt your coin 10 degrees before flipping, or flip in a clockwise rotation, the correlations you observe are bounded. There is a maximum amount of correlation that pre-programmed coins can produce, no matter how elaborate the programming. And quantum mechanics predicts that entangled particles can exceed that maximum. Let me expand on Bell's theorem a little, because the logic is so beautiful and so important that it deserves to be understood carefully. The key idea is this. Suppose Einstein is right, and there are hidden variables. Suppose that when 2 entangled particles are created, they carry with them a shared set of instructions, like a pair of sealed envelopes containing pre-agreed answers.
The instructions determine what happens when each particle is measured along any direction. The particles do not need to communicate, they already know what to do. Now, for the simplest case, both measurements along the same axis, this hidden variable model reproduces quantum mechanics perfectly. If you measure both spins along the vertical axis, you always get opposite results, up and down or down and up. A hidden variable model handles this easily. The instructions just say, if measured vertically, particle A gives up and particle B gives down, or vice versa, randomly for each pair. The trouble starts when you measure the particles along different axes. Suppose you measure particle A along the vertical axis and particle B along an axis tilted at 60 degrees. Now the correlations are more subtle. Quantum mechanics makes a precise prediction for the probability that the two measurements agree or disagree, and that prediction depends on the angle between the measurement axes. Bell's stroke of genius was to show that any hidden variable model, any model where the particles carry pre-programmed instructions, must satisfy a specific mathematical inequality relating the correlations at different angles. The inequality is remarkably simple. It involves just the probabilities of agreement or disagreement at three different angles. And Bell proved, rigorously, that no assignment of hidden variables, no matter how cleverly designed, can violate this inequality. Then he showed that the quantum mechanical predictions do violate it. The maximum violation of Bell's inequality predicted by quantum mechanics occurs when the measurement axes are separated by specific angles. For the most common version of the inequality, the CH-SH inequality, which is a slightly more practical reformulation, the hidden variable bound is 2, and the quantum mechanical maximum is 2 times the square root of 2, which is about 2.83. That is a 41% excess, not a tiny, marginal, barely detectable effect, a whopping, unmistakable violation. When Alain Aspect performed the definitive experiment in Paris in 1982, his results matched the quantum prediction exactly. The correlations exceeded the Bell bound, and, critically, Aspect's experiment included a feature that previous tests had lacked. He changed the measurement settings after the particles had already been emitted, using fast switching devices that redirected each particle to one of 2 detectors at random. This closed the locality loophole, the possibility that the particles could somehow signal each other about the measurement settings in advance. The settings were chosen after the particles were in flight, and the measurements were completed in less time than light would need to travel between the 2 detectors. No signal, no influence, no communication could explain the correlations. And yet the correlations were there. Since Aspect's experiment, the tests have become more and more stringent. In 2015, a group in Delft, led by Ronald Hansen, performed what is widely considered the first truly loophole-free Bell test. They used entangled electrons in diamond crystals separated by about 2/3 of a mile, with the measurement settings determined by events in distant parts of the universe. Random number generators seeded by the cosmic microwave background radiation to eliminate even the most exotic loopholes. The result was the same. Bell's inequality was violated. The quantum prediction was confirmed. The implications are profound and still being digested by the physics community. There is a way to make the entanglement phenomenon even more vivid, using an analogy that was presented in a Nova documentary about quantum physics. Think about it this way. Imagine a machine that produces pairs of coins. You take one coin, your friend takes the other, and you each go to opposite sides of the planet. You each flip your coin. For any single flip, the result is completely random, heads or tails, 50-50. If you just looked at your own results, you would see a perfectly random sequence, nothing strange at all. But when you compare your results with your friends, coin by coin, something astonishing appears. Every time you got heads, your friend got heads. Every time you got tails, your friend got tails. 100% correlation every single time. Now you might think, well, They are just matched coins. The machine programmed them in advance. Both coins in each pair were set to show the same face. That is the hidden variable explanation, and it works perfectly for this simple case. But here is where Bell's theorem bites. What if, instead of just flipping the coins normally, you can also tilt them before flipping, say 10 degrees or 20, or any angle you choose?
And what if the correlations you observe depend on the relative angle between your tilt and your friend's tilt? Bell's theorem says that if the coins are pre-programmed, the correlations must obey a certain limit. And quantum mechanics predicts correlations that exceed that limit. The experiments confirm the quantum prediction. The correlations are too strong to be explained by pre-programming. And since the coins are on opposite sides of the planet, or in the lab, separated by enough distance that light cannot travel between them during the measurement, no signal can explain it either. The universe is doing something that has no classical analog. Two particles, separated by any distance, are connected in a way that defies both our intuition about locality and our intuition about predetermined outcomes. And here is one more startling fact. The equations of quantum mechanics give us no reason to think that entanglement has a distance limit.
It should work across a room, across a continent, across the solar system, across the galaxy. The question was asked in the Nova documentary. Does entanglement work between here and the Andromeda galaxy? The physicists' answer was, probably. The equations give us no reason to think it would not. Entanglement is now being actively exploited in technology. Quantum cryptography uses entangled photons to create encryption keys that are provably unbreakable. Not unbreakable because the math is hard, but unbreakable because any attempt to eavesdrop disturbs the quantum state and reveals the intruder. Quantum computing uses entanglement to perform certain calculations exponentially faster than classical computers. The qubit, the fundamental unit of quantum information, is just a quantum system with two states, exactly the kind of system we were discussing in the spin chapter. And when qubits become entangled, they can explore many computational paths simultaneously, exploiting the full weirdness of quantum mechanics for practical purposes. And improvements to LIGO, the gravitational wave observatory, use squeezed quantum states, a form of carefully engineered entanglement to push the sensitivity of the laser interferometer beyond what classical physics would allow. Quantum mechanics, once a source of confusion and philosophical debate, has become a tool for engineering, a resource to be harnessed and exploited. But the foundational questions remain. What is the wave function? What happens when you measure? What is really going on when two particles are entangled? Not by a tiny amount. The quantum prediction is about 40% higher than the local hidden variable bound for certain measurement settings. When the experiments are done, the quantum prediction wins. The correlations are stronger than any pre-programming can explain.
So what does this mean? What is actually happening? The honest answer is that nobody knows, not in the sense of having a universally accepted picture, but the experimental facts constrain the options severely. One option is to give up locality, accept that a measurement on one particle does somehow instantaneously influence the other particle, regardless of the distance between them. Many physicists lean toward this interpretation, although the word influence is slippery. It does not mean you can send a message faster than light. The correlations between entangled particles, while real and instantaneous, cannot be used to transmit information. If you have only one entangled particle and no way to communicate with the person who has the other one, your measurement results look perfectly random. You cannot tell whether the other particle has been measured or not. The correlation only becomes visible when you compare results later, and that comparison requires ordinary, slower-than-light communication. Another option is to give up realism. Accept that particles genuinely do not have definite properties before measurement, and that the correlations between entangled particles arise because the two particles are described by a single, indivisible quantum state,
not two separate states. In this view, asking, "What is the spin of the Tokyo particle before I measure it?" is a meaningless question. The particle does not have a spin until the measurement creates one. A third option, which we will come to shortly, is to accept that both particles do have definite outcomes, but only in the context of a branching universe where both outcomes occur in different branches. This is the many worlds interpretation, but regardless of which interpretation you favor, the experimental facts are clear. The universe is non-local in some deep and fundamental sense. The correlations between entangled particles are real. They are stronger than any classical mechanism can explain, and they have been confirmed to extraordinary precision. Sean Carroll, the theoretical physicist at Johns Hopkins, put it well in a conversation about entanglement. He pointed out that quantum mechanics is a monist theory. In classical mechanics, you describe each particle separately. You say this particle is here, that particle is there. Each particle has its own independent state. But in quantum mechanics, there is a single state for the whole system. For two entangled particles, you cannot describe the state of one without reference to the other. There is no separate state for the London particle and no separate state for the Tokyo particle. There is only the combined state, and the combined state encodes correlations that cannot be decomposed into individual properties. And in fact, taking this to its logical conclusion, there is a single quantum state for the entire universe. One wave function. One mathematical object that encodes everything. Your job, as a physicist or as a person trying to understand the world, is to carve that wave function up into pieces that correspond to the things you observe. Electrons, atoms, tables, cats, planets. But the carving is something you do. The underlying reality is one thing. There is something almost dizzying about that idea, and I think it is worth sitting with it for a moment, especially at this point in the evening when the world is quiet and it is just you and these ideas. Every particle that makes up your body was once entangled with other particles. The atoms in your hand were forged in the cores of stars that exploded billions of years ago, scattering their contents across space, and those atoms interacted with countless others along the way, becoming entangled and disentangled in an unimaginably complex web of quantum correlations. The idea that you are a separate, self-contained thing, distinct from the rest of the universe, is a classical approximation. At the quantum level, the boundaries blur. The universe is not a collection of separate objects. It is one enormously complicated, deeply interconnected quantum state. And that brings us to the final question, the one that all the others have been building toward. If quantum mechanics is true, and every experiment ever performed says it is, then what is it telling us about the nature of reality? What is really going on out there, behind the mathematics, behind the probabilities, behind the wave function? Because it turns out that the math of quantum mechanics is not the controversial part. Everyone agrees on the math. Everyone agrees on what the theory predicts. The controversy is about what it means. The question that physics still cannot answer. Let me begin this final chapter by stating something that might surprise you given everything we have discussed tonight. Quantum mechanics is finished. As a mathematical framework, as a set of rules for making predictions, it is done, complete. It has been done since about 1927, with refinements through the 1940s and 50s. Every experiment that has ever been performed has confirmed its predictions, often to 12 or more decimal places of accuracy. It is the most successful quantitative theory in the history of science. There is no empirical result that contradicts it. There is no measurement that deviates from what it says should happen. And yet, there is something missing, something that does not sit well. Something that has been debated, sometimes bitterly, for almost 100 years. The math tells you what will happen when you make a measurement. It tells you the probabilities of every possible outcome, and those probabilities are always right. But the math does not tell you what is happening when you are not making a measurement. It does not tell you what the electron is doing between the moments you look at it. It does not tell you how the wave function, which evolves smoothly and deterministically, suddenly produces a single definite result when you observe it. It does not tell you what measurement even means, physically, at the level of particles and fields. These are not fringe questions. They are not asked only by philosophers or science fiction writers. They are asked by working physicists who use quantum mechanics every day and find themselves unable to agree on what it is describing. And the remarkable thing is that there are several completely different answers, several completely different pictures of what the theory means, and all of them make exactly the same experimental predictions. You cannot distinguish between them by doing an experiment. At least, not yet. Possibly not ever. Each one accepts the same math and the same predictions, but tells a radically different story about what is going on behind the curtain. Let me walk through the main ones, because they are fascinating, and because each one reveals something about how far we have traveled from the orderly, deterministic universe that Laplace dreamed of at the dawn of the 19th century. The Copenhagen interpretation. This is the oldest and still the most commonly taught interpretation. It was developed primarily by Niels Bohr and Werner Heisenberg in the 1920s in Copenhagen at Bohr's Institute, and it bears the name of that city. The Copenhagen interpretation says, roughly, the following. The wave function is not a description of reality. It is a tool for calculating the results of measurements. Before you measure a particle's position, the particle does not have a position. Before you measure its spin, it does not have a spin. These properties come into existence at the moment of measurement, and the wave function tells you the odds of what you will find. As for what happens between measurements, what the particle is doing when nobody is looking, the Copenhagen interpretation says that this is not a meaningful question. You cannot observe the particle between measurements, and therefore asking about its state between measurements is asking a question that physics cannot and should not attempt to answer. Measurement is a special process, distinct from the normal evolution of the wave function. When you measure, the wave function collapses. When you do not measure, it evolves smoothly. These are two different rules, and the Copenhagen interpretation does not try to unify them or explain why one transitions to the other. It just says, those are the rules, apply them and you will get the right answers. This is deeply unsatisfying to many physicists. Sean Carroll has described the Copenhagen interpretation in vivid terms, calling it, quote, a god-awful mess that nobody would accuse of being very beautiful. And the reason for that harshness is clear. The Copenhagen interpretation draws a line between the quantum world of particles and the classical world of measuring devices and human observers. And it never explains where that line is or why it exists. It says, measurement causes collapse, but it does not tell you what counts as a measurement. Is it when a photon hits a detector? When the detector sends a signal? When a human looks at the signal? When the human's brain processes the information? At each of these stages, you could in principle describe the process using quantum mechanics, with no collapse at all. The collapse is imposed from outside the theory, as an additional postulate, and it never feels fully justified. And yet, for practical purposes, Copenhagen works beautifully. If you just want to calculate the spectrum of an atom, the probability of a particle tunneling through a barrier, the conductivity of a semiconductor, or the behavior of a laser, Copenhagen gives you the recipe. Shut up and calculate, as the physicist David Mermin famously summarized the attitude. Do not ask what it means. Just do the math and build the machine. Most working physicists, if pressed, will admit that they use some version of this approach in their daily work. Whether they believe it as a description of reality is another matter. The many worlds interpretation. The most radical alternative to Copenhagen was proposed in 1957 by a young American graduate student named Hugh Everett III, working at Princeton under the supervision of John Archibald Wheeler. Everett looked at the measurement problem and asked a simple question. What if the wave function never collapses? What if the Schrödinger equation is always correct, without exception, and the collapse is just an illusion? To see where this leads, go back to the Stern-Gerlach experiment. An electron is in a superposition of spin-up and spin-down. You measure it. According to Copenhagen, the wave function collapses and you get one outcome. According to Everett, no collapse occurs. Instead, you, the observer, become entangled with the electron.
The wave function of the combined system, electron plus you, evolves into a superposition of two branches. One branch, where the electron is spin-up and you saw spin-up, and another branch, where the electron is spin-down and you saw spin-down. Both branches are real, both continue to exist, but they no longer interact with each other. They are, in a sense, transparent to each other. Each branch goes on evolving independently, each one containing a version of you with a consistent memory of a definite measurement outcome. You, the person who saw spin-up, have no way of knowing about or communicating with the other version of you who saw spin-down. This is many worlds. The implications are staggering. Every quantum measurement, every interaction that produces a superposition, causes the universe to branch. The number of branches is unfathomably large. Not infinite exactly, but so large that very, very, very big barely begins to describe it.
And each branch is as real as the one you experience. Where are these other worlds? This is the question everyone asks, and the answer is counterintuitive in the extreme. The worlds are not in different places in space. Space exists separately within each world. The worlds are not parallel dimensions floating next to ours. They are different components of a single, enormously complex mathematical object, the universal wave function, that lives in an abstract space called Hilbert space. Sean Carroll, who is one of the most prominent advocates of the many worlds interpretation today, explained it in a conversation with remarkable clarity. He pointed out that many worlds is what you get if you simply take the Schrödinger equation seriously. The Schrödinger equation was invented to fit experimental data. It works. Everyone agrees it works. The Copenhagen interpretation modifies the equation by adding a collapse rule that contradicts the equation's normal behavior.
Many worlds just says, trust the equation. Do not add anything extra. The equation predicts branching, so there is branching. When people object that they have never experienced being in a superposition, Everett's response was elegant. He said, "The problem is not with the Schrödinger equation. The problem is that you have misidentified yourself in the wave function. You are not the superposition. You are one branch of it. The part of the wave function where the spin was up is completely disconnected from the part where the spin was down. They do not interact. They do not influence each other. So you should identify yourself as one branch, not both. And in your branch, you see a definite outcome, just as experiments always show." Carroll has described many worlds as the most austere, cleanest, no extra baggage theory of quantum mechanics. It adds nothing to the standard mathematical framework. It only subtracts. It subtracts the collapse postulate.
And what you get in return is a picture of reality that is internally consistent, fully deterministic at the level of the universal wave function, and compatible with everything we observe. The price is ontological extravagance. You have to accept that every quantum event spawns a branching tree of realities, each one as real as yours. You have to accept that there are versions of you who made different choices, saw different measurement outcomes, lived different lives, all coexisting in the vast space of the wave function. And you have to develop new philosophical frameworks for thinking about probability and identity in a setting where every possible outcome actually occurs. Carroll acknowledged this openly. He said that the single best reason to be skeptical about many worlds is not that it does not make sense, or that it contradicts data, or that the other worlds cannot be found. The best reason is that accepting it requires new philosophy.
A new way of thinking about what it means to be you, what probability means when every outcome happens, and how to make predictions in a deterministic universe where randomness is an illusion. He has described this work as very doable, but not straightforward. And he has said, with a smile, that people who reject many worlds are simply wimping out. Hugh Everett himself did not get to see his idea vindicated. His thesis was essentially ignored when it was published. Bohr dismissed it when John Wheeler brought it to Copenhagen. Everett, discouraged, left physics altogether. He worked for the Pentagon on classified defense research, became overweight, drank heavily, and died of a heart attack in 1982 at the age of 51. His daughter Elizabeth also struggled deeply and died in 1996. She reportedly expressed a wish to join her father in another universe. The idea that Everett had proposed at 27 resurfaced in the 1970s, championed by the physicist Bryce DeWitt, who gave it the catchy name Many Worlds. It has been growing in influence ever since, and today surveys of physicists show that it is roughly as popular as the Copenhagen interpretation, though opinion polls are a poor way to settle questions about the nature of reality. The pilot wave theory. There is a third option, one that goes back to Louis de Broglie and was later revived by the American physicist David Bohm. It is called the pilot wave theory, or de Broglie-Bohm theory, and it offers something that neither Copenhagen nor Many Worlds provides: a picture of particles as real things, with definite positions at all times, following definite trajectories through space. In this theory, there is a wave function, and it evolves according to the Schrödinger equation, just as in standard quantum mechanics.
But there are also particles, actual point-like objects, and they are guided by the wave function. The wave function acts as a pilot wave, pushing the particles along specific paths. The particles always have definite positions. There is no superposition of particle locations. The randomness in quantum measurements arises because we do not know the exact initial positions of the particles, not because the positions are genuinely undefined. In the double-slit experiment, the pilot wave goes through both slits and creates an interference pattern. The particle goes through only one slit, but it is guided by the wave to a final position that reflects the interference pattern. So the pattern builds up over many particles, just as observed, even though each individual particle goes through a single slit. The catch, and it is a significant one, is that the pilot wave is non-local. When two particles are entangled,
the pilot wave of one depends instantaneously on the position of the other, no matter how far apart they are. This allows the theory to reproduce the correlations that violate Bell's inequality, because the theory explicitly abandons locality. It keeps realism. Particles have definite properties at all times, but it gives up on the idea that influences cannot travel faster than light. Einstein, ironically, would probably not have been satisfied with this solution. He valued locality at least as much as he valued realism. Giving up locality to save realism would not have been a trade he wanted to make. Let me go a little deeper into the Copenhagen interpretation, because despite its dominance in textbooks, it has problems that are worth understanding clearly. The central issue is the Heisenberg cut, the dividing line between the quantum world and the classical world.
on one side of the cut, things are described by wave functions and superpositions and the Schrödinger equation. On the other side, things are described classically, with definite properties and definite states. The measurement apparatus sits on the classical side. The quantum system sits on the quantum side. And when they interact,
the wave function collapses. But where exactly is the line? The Copenhagen interpretation does not say. It cannot say because there is no physical criterion for distinguishing a quantum interaction from a classical measurement. An electron interacting with a photon in empty space is a quantum process described by the Schrödinger equation. An electron interacting with a photon in a Geiger counter is a measurement that causes collapse. Both interactions involve the same fundamental forces and the same fundamental particles. The difference is not physical. It is a matter of human convention. We decide what counts as a measurement based on what we consider to be a macroscopic device with a readable output. John Bell, the same Bell who proved the theorem about entanglement, was deeply troubled by this. He wrote a famous essay called Against Measurement, in which he argued that the word measurement has no place in the foundations of a fundamental physical theory. If quantum mechanics is supposed to describe all of physics, then it should describe measuring devices too, and observers too, and the entire universe too. And in a theory that applies to the entire universe, there is no external observer to trigger collapse, because everything is inside the system. This is the problem that motivated Everett, and it is worth understanding why his solution is so compelling to many physicists, despite its radical implications.
In the Copenhagen picture, there are two kinds of physical evolution: smooth Schrödinger evolution, Rule 1, and discontinuous collapse, Rule 2. Everett dispenses with Rule 2. There is only Rule 1. The Schrödinger equation applies everywhere, always, without exception. There is no collapse. There is no Heisenberg cut. There is just the universal wave function evolving deterministically and continuously according to a single equation. The price is that the universal wave function develops many branches, each one corresponding to a different measurement outcome. In each branch, an observer sees a definite result. The observer in that branch has memories consistent with that result and perceives no superposition. From the inside, each branch looks perfectly classical. The strangeness is not inside any branch. It is in the existence of the other branches. Carroll explained the logic with a clarity that is worth following closely.
Start with a simple setup: an electron in a superposition of spin up and spin down, and a detector that measures the spin. Before the measurement, the state of the universe is electron, superposition of up and down, detector, ready to measure, observer, waiting to see the result. Now apply the Schrödinger equation. The electron interacts with the detector, and the detector interacts with the observer. The final state is electron up, detector reads up, observer sees up, superposed with electron down, detector reads down, observer sees down. This is just the Schrödinger equation doing its thing. No new physics, no collapse. Everyone agrees this is what the equation says. The Copenhagen advocate then says, and now collapse happens. One branch disappears, and you end up in the other one. Everett says, both branches persist, neither one disappears. The reason you do not experience a superposition is that you are in one branch, not both.
The observer who saw up is not aware of the observer who saw down, because the two branches do not interact. They have decohered, the technical term for the process by which quantum superpositions become effectively irreversible at the macroscopic level. Decoherence is a crucial concept. It was developed primarily in the 1970s and 80s by physicists like Heinz-Dieter Zeh and Wojciech Zurek, and it provides a physical mechanism for why macroscopic objects do not exhibit visible quantum behavior. The idea is that any macroscopic object interacts with a huge number of environmental particles, air molecules,
photons, stray electrons, and those interactions rapidly entangle the object with its environment in a way that makes the different branches of the superposition lose phase coherence. They can no longer interfere with each other. For all practical purposes, the superposition has decayed into a classical mixture.
Decoherence does not solve the measurement problem by itself.
It does not explain why you see one outcome rather than another. But it does explain why macroscopic objects look classical. It closes the gap between the quantum world and the everyday world without requiring a Heisenberg cut or a separate collapse postulate. And it is a real physical process that has been observed and measured in the laboratory. In the many worlds picture, decoherence is what causes branching. When a quantum system interacts with a macroscopic environment, the superposition decoheres into branches that no longer interfere. Each branch contains a classical-looking world with definite measurement outcomes. The branching is not instantaneous, and it is not perfectly sharp. It is a rapid, smooth, physical process, driven by the sheer number of environmental particles involved. Now, there is a question that many people ask at this point, and it is a good one.
If every outcome of every quantum measurement actually happens, then what does probability mean?
In the many worlds interpretation, every outcome has probability 1. It definitely happens in some branch. So what does it mean to say that the probability of spin-up is 50%? This is the main philosophical challenge facing many worlds, and Carroll was frank about it. He said that making sense of probability in a many worlds context requires new philosophy. It requires rethinking what probability means for a branching universe. Various proposals have been put forward: self-locating uncertainty, decision theoretic arguments, density matrix weighting. And Carroll believes the problem is solvable, but he acknowledged it is not yet fully solved. And then there is the question of identity. When the universe branches, is the observer before the measurement the same person as the observer after? Which branch do you end up in? These are questions that classical physics never had to deal with, and they require careful philosophical work to resolve. Carroll said something in his conversation that I think captures the right attitude. The best reason to be skeptical about many worlds is not scientific. It is philosophical. It is the recognition that accepting many worlds requires a grand extrapolation, far beyond what we can observe, into territory that demands new ways of thinking about ourselves and our place in reality. And he said, with characteristic directness, that people who reject many worlds on these grounds are being methodologically conservative, which he considers a polite way of saying they are wimping out. Whether you agree with that assessment or not, you have to admire the audacity of the proposal.
A graduate student in the 1950s, 27 years old, proposed that every quantum measurement splits the universe, that there are uncountably many versions of you, living uncountably many different lives, and that all of this follows logically from taking the Schrödinger equations seriously. His idea was dismissed, he left physics, and he died in obscurity. And now, nearly 70 years later, his interpretation is one of the most influential in all of physics, advocated by some of the leading theorists in the world. That is quite a legacy for a 27-year-old's doctoral thesis. Other approaches. There are additional interpretations. Objective collapse theories, proposed by physicists like Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber, the GRW theory, and later by Roger Penrose, suggest that the wave function really does collapse, not because of measurement, but because of some physical process that we have not yet identified. Perhaps gravity causes it. Perhaps there is a new law of physics, below the scale we have tested,
that causes superpositions to spontaneously decay into definite outcomes. These theories make slightly different predictions than standard quantum mechanics, and experiments are being designed to test them. And there is cubism, or quantum Bayesianism, which says that the wave function is not a description of the world at all. It is a description of your beliefs, your personal expectations about what you will observe next. Quantum mechanics, in this view, is not about reality. It is about you, the agent, making predictions in an uncertain world. Different observers can have different wave functions for the same system because they have different information, and both can be right. Reality is not observer-independent. It is agent-relative. Each of these interpretations has its advocates and its critics. Each one resolves some puzzles and creates others.
And the remarkable thing, the thing that makes this situation truly unique in the history of science, is that they all make the same predictions for every experiment that has been performed or proposed. They are empirically equivalent, at least for now. You cannot distinguish them by looking at the world. You can only distinguish them by thinking about the world. Sean Carroll made a remark in a conversation that I keep coming back to. He said that the single most interesting surprise to him would be if quantum mechanics itself was somehow superseded by something better. As far as he knows, there is no empirical reason to think that quantum mechanics is not 100% correct. But it might not be. And if there is a crack, if there is a place where quantum mechanics breaks down, where its predictions deviate from reality, the most likely place to find that crack is at the intersection of quantum mechanics and gravity, black holes, the Big Bang.
The extreme conditions where both quantum effects and gravitational effects matter, and where the two great theories of 20th century physics, quantum mechanics and general relativity, come into conflict. Because quantum mechanics and general relativity, as they currently stand, are incompatible. They cannot both be exactly right. General relativity describes gravity as the curvature of space-time, a smooth, continuous geometry. Quantum mechanics describes everything else in terms of wave functions and probabilities and discrete quanta. When you try to apply quantum mechanics to gravity itself, when you try to quantize space-time, you get nonsensical results. Infinities that cannot be removed, predictions that make no sense. The search for quantum gravity, a theory that unifies quantum mechanics and general relativity into a single framework, is the great open problem of fundamental physics. String theory is one approach. Loop quantum gravity is another. The holographic principle, which suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary, is a clue that has generated enormous excitement and hundreds of papers. And black holes sit right at the center of this puzzle. When something falls into a black hole, its information, the quantum state that described it, seems to be lost. But quantum mechanics says information cannot be destroyed. Stephen Hawking showed in the 1970s that black holes radiate particles and slowly evaporate, which makes the problem even worse. Once the black hole is gone, where did the information go? Most physicists today believe that the information somehow escapes in the Hawking radiation, but nobody has a complete, convincing explanation of how. This is the black hole information paradox, and it is one of the deepest unsolved problems in physics. Its resolution, when it comes, may require a fundamental revision of our understanding of space, time, and quantum mechanics itself. And that brings us back to the question that started this whole journey. The question of what quantum mechanics means. Because the answer to that question may depend on physics we have not yet discovered. The correct interpretation of quantum mechanics may not be any of the ones we currently have. It may be something that only becomes clear once we understand quantum gravity, once we see how the quantum world and the gravitational world fit together, once we understand what happens at the singularity inside a black hole, or at the first instant of the Big Bang. We do not know yet. And there is something both humbling and strangely beautiful about that. We have the most successful scientific theory ever created. It governs every piece of technology in modern life.
Your phone, your computer, the GPS that guides your car, the laser that reads your music, the MRI machine that images your brain. All of these work because quantum mechanics works. The theory is not speculative. It is not tentative. It is battle-tested to an extraordinary degree. And yet, after 100 years, we still do not know what it is telling us about the nature of reality. The people who built it, Planck, Einstein, Bohr, Heisenberg, Schrödinger, Born, Dirac, Feynman, disagreed with each other profoundly about what they had constructed. Einstein went to his grave believing it was incomplete. Bohr went to his believing it was complete, but that asking what happens between measurements was illegitimate. Schrödinger, who wrote down the central equation of the theory, was so unhappy with its interpretation that he said he wished he had never had anything to do with it.
Let me also add a few more threads to the story, because there are aspects of quantum mechanics that we have touched on but not fully explored, and they connect everything together in ways that are worth seeing. The first is the quantum of action itself. We have mentioned Planck's constant many times, in the blackbody formula, in the photoelectric effect, in de Broglie's wavelength, in the uncertainty principle, in the path integral. But let me now pull all of those threads together, because the unifying role of Planck's constant is one of the deepest and most beautiful features of quantum mechanics. Planck's constant has units of joule seconds, which is the same as energy times time, or momentum times distance, or angular momentum. All of these combinations are different manifestations of the same physical dimension, action. And every time Planck's constant shows up in quantum mechanics, it is playing the same fundamental role. It is setting the scale of the quantum. In the blackbody problem, the quantum of energy is hf, Planck's constant times frequency. The energy of a single quantum of radiation is determined by the action constant. In the photoelectric effect, each photon carries energy hf, and the kinetic energy of the ejected electron depends on how much energy the photon has left over after paying the exit fee. Again, Planck's constant determines the energy scale. In de Broglie's formula, the wavelength of a particle is h divided by momentum. Planck's constant bridges the wave description, wavelength, and the particle description, momentum. In the uncertainty principle, the product of the uncertainty in position and the uncertainty in momentum is at least h bar over 2. Planck's constant sets the minimum fuzziness of the quantum world. In Bohr's model, the allowed angular momenta are integer multiples of h bar. Planck's constant quantizes the orbits. In the path integral, the phase accumulated along a path is the action divided by h bar. Planck's constant determines how rapidly the phases spin, and therefore how quickly the contributions from different paths cancel. And in the Schrödinger equation itself, Planck's constant appears on both sides, connecting the time evolution of the wave function to the energy of the system. One number. One tiny, almost inconceivably small number. And it shows up everywhere, in every equation, in every formula, connecting every aspect of quantum mechanics to every other aspect. It is the thread that runs through the entire tapestry. If Planck's constant was 0, there would be no quantum mechanics. Energy would be continuous. Light would be purely a wave. Particles would have definite trajectories. The uncertainty principle would disappear, and the world would be perfectly classical. The fact that it is not 0, the fact that it has a small but finite value, is what makes the quantum world real. And nobody knows why it has the value it does. There is no derivation, no theoretical argument, no deeper principle from which the value of Planck's constant can be calculated. It is a measured number, determined by experiment, and as far as we know, it could have been anything. If it were much larger, Quantum effects would be visible in everyday life, and the world would be a very strange place. Objects would tunnel through walls, particles would spread out into visible waves, and the definite, solid, predictable world we are used to would dissolve into quantum fuzz. If it were much smaller, quantum effects would be confined to even tinier scales than they currently are, and it would have taken even longer for physicists to discover them. The second thread I want to pick up is the practical impact of quantum mechanics. Because it is easy, lying here in the dark thinking about philosophy and interpretations, to forget that quantum mechanics is not just an abstract theory. It is the foundation of modern technology. The transistor was invented in 1947 at Bell Labs by John Bardeen, Walter Brattain, and William Shockley. Its operation depends entirely on the quantum mechanical properties of semiconductors, the way electrons occupy energy bands in crystalline materials, the way junctions between differently doped semiconductors allow current to flow in one direction but not the other. Without quantum mechanics, there are no transistors. Without transistors, there are no computers. Without computers, there is no modern world, no internet, no smartphones, no GPS, no digital music, no satellite communications, no medical imaging. The digital revolution, every bit of it, is built on the foundation of quantum mechanics. Lasers are another quantum technology. The acronym stands for Light Amplification by Stimulated Emission of Radiation, and the word stimulated emission refers directly to a process first described by Einstein in 1917. When a photon of the right frequency passes by an excited atom, it stimulates the atom to emit a second photon that is identical to the first. Same frequency, same phase, same direction. This is a quantum process. It has no classical analog, and from it we get the purest, most coherent light sources ever created. Sources that enable everything from fiber optic communications to laser surgery, to barcode scanners, to gravitational wave detection. MRI scanners, magnetic resonance imaging, depend on the quantum mechanical spin of hydrogen nuclei in your body. When placed in a strong magnetic field and stimulated with radio waves at the right frequency, these nuclei absorb and re-emit energy in patterns that can be decoded to produce detailed images of soft tissue. The entire technique is quantum mechanical from start to finish. The atomic clocks that set the standard for timekeeping worldwide use the quantum properties of cesium or strontium atoms. As explained in the Nova documentary, these clocks exploit the fact that the resonant frequency of a particular atomic transition is the same everywhere in the universe, determined by quantum mechanics with extraordinary precision. The best current atomic clocks use strontium atoms trapped in optical lattices, interrogated by laser light tuned to one of strontium's resonant frequencies. The physicist Jun Ye at the Boulder, Colorado laboratories of NIST described the process beautifully. The laser puts the strontium electron into a superposition of its ground state and its excited state, creating what Ye calls a quantum pendulum that oscillates at nearly 1 million billion cycles per second. This frequency is so high that even tiny changes in the gravitational field, changes caused by raising the clock by the width of a human hair, produce a measurable difference in the rate of time. General relativity, confirmed by quantum mechanics. And then there is LIGO. The Laser Interferometer Gravitational Wave Observatory uses laser light, split along two perpendicular arms, each 2.5 miles long, to detect distortions in the fabric of space-time caused by gravitational waves from merging black holes and neutron stars. The precision required is staggering. LIGO can detect changes in the length of its arms that are thousands of times smaller than the diameter of a proton. This precision is possible only because of the extraordinary coherence of laser light, a coherence that is a direct consequence of quantum mechanics, and recent upgrades to LIGO use quantum squeezed states, a technique that exploits the uncertainty principle to reduce noise in one measurement variable at the expense of another, to push beyond the classical limits of detection. Quantum mechanics, born from the puzzle of how hot objects glow, now listens to the ringing of space-time itself.
The first gravitational wave event, detected by LIGO in September 2015, was the merger of two black holes about 36 and 29 times the mass of the Sun, roughly 1.3 billion light-years away. In the final fraction of a second before they merged, these two black holes released more energy in gravitational waves than all the stars in the observable universe combined. And we heard it through a device that depends, at its core, on the physics that Max Planck reluctantly introduced on a December afternoon in 1900. So that is where we are. 6 experiments, 6 assumptions overturned. Energy is discrete. Light is both wave and particle. Particles explore every possible path. Properties do not exist until measured. Entangled particles are correlated in ways that no classical mechanism can explain. And the meaning of the theory that describes all of this is still, after a century, an open question.
And right now, as you lie there in the dark, every single one of these strange quantum facts is at work inside your body. The phone you might have set down on the nightstand, its screen was made possible by quantum mechanics. The LEDs emit photons at specific frequencies because electrons in semiconductor materials jump between quantized energy levels, exactly the kind of jumps that Bohr first described in 1913. The transistors in the processor are so small that quantum tunneling, particles passing through barriers they classically should not be able to cross, is a factor that engineers have to account for. The GPS signal that guided you home tonight depends on atomic clocks, clocks that use the quantum properties of cesium atoms to tick with a precision of 1 second in 300 million years. But it goes deeper than technology. The chemistry that keeps you alive is quantum mechanical. The bonds between the atoms in your DNA are quantum bonds, governed by the wave functions of electrons in molecular orbitals. The enzymes that are digesting your dinner right now work by quantum tunneling of protons. The oxygen molecules that your hemoglobin is carrying through your bloodstream are held together by a quantum mechanical bond that is impossible to explain with classical physics. Molecular oxygen is paramagnetic, with 2 unpaired electrons, a fact that baffled chemists for decades until quantum mechanics explained it. Your brain right now is producing electrical signals, and those signals ultimately depend on the flow of ions through protein channels in your neurons, channels whose selectivity is determined by the quantum mechanical size of the ions and the quantum mechanical properties of the protein structure.
When those signals slow down, when the thalamus begins to gate the sensory information coming in, and the cortex begins to settle into the slower rhythms of sleep, that transition is governed by the same fundamental laws that Planck first stumbled upon in 1900. The pillow under your head is made of atoms that are almost entirely empty space. The nucleus of each atom is 10,000 times smaller than the atom itself. If you could somehow remove all the empty space from the atoms in your body, the remaining matter would fit inside a single grain of sand. You feel solid because of quantum mechanics, because the electrons in the atoms of your skin repel the electrons in the atoms of the pillow, not through contact in the classical sense, but through the Pauli exclusion principle, a quantum mechanical rule that forbids 2 electrons from occupying the same state.
Your sense of solidity, the feeling of the mattress beneath you, the weight of the blanket on your chest, all of it is a quantum effect. A consequence of the wave nature of the particles that make up everything you can touch. And the light coming through your window, the photons from a street light or from the moon, each one was created by a quantum transition in an atom somewhere. An electron jumping from a higher energy level to a lower one, releasing a photon of a specific frequency, a specific color. Each photon traveled as a wave, exploring all possible paths from the source to your window, and the overwhelming majority of those paths cancelled each other out through destructive interference, leaving only the classical path, the straight line from the light source to your eye. But all those other paths were real. The paths that went to the edge of the solar system and back were real. The paths that zigzagged through the atmosphere were real. They all contributed to the sum.
They just happened to cancel, leaving the photon traveling in what looks like a straight line. This is the world. This is the actual, experimentally verified, technologically exploited, deeply strange world that you live in. A world where energy comes in lumps, where light is both wave and particle, where every object explores every possible path, where properties do not exist until measured, where particles separated by galaxies are correlated in ways that no signal can explain, and where the very meaning of reality itself is still being debated by the most brilliant minds on the planet. And the thing that I find most remarkable about all of it, the thing that makes me pause every time I think about it, is that this is happening right now. Not in some distant laboratory, not in some abstract mathematical space. Right now, inside you, around you, beneath you. The atoms in your body are following the rules of quantum mechanics this very second.
The photons entering your eyes are quantum objects. The electrical signals in your brain are quantum processes. The chemical bonds holding your molecules together are quantum effects. You are a quantum mechanical system, the most complex and intricate quantum system that, as far as we know, has ever existed on this planet. And all you have to do, right now, is rest. The questions will still be there in the morning. The wave functions will still be evolving. The experiments will still be confirming the theory. The physicists will still be arguing about what it all means. And somewhere, in a laboratory, someone is setting up a new experiment, testing a new idea, pushing a little further into the mystery. But tonight, you do not have to push anywhere. You do not have to understand everything. You do not have to pick an interpretation or choose a side. You can just let the ideas soften and blur at the edges, the way the wave function spreads out when you stop observing it.
Let your breathing slow down. Let the pillow absorb the weight of your head. Let the quiet, electromagnetic hum of the universe do what it has been doing for 13.8 billion years. And there is something else that is worth mentioning, because it connects the very first experiment we discussed tonight to the very last. Remember the blackbody spectrum, the puzzle of why hot objects glow the way they do. The light coming from a hot filament is thermal radiation, photons emitted by atoms vibrating at various frequencies. Each photon carries energy h times f, and the spectrum of radiation reflects the statistical distribution of those photons at a given temperature. Now think about the cosmic microwave background, the faint thermal radiation that fills the entire universe, left over from the Big Bang. It has a temperature of about 2.7 Kelvin, just a few degrees above absolute zero, and its spectrum is a perfect blackbody spectrum, the most perfect blackbody ever measured. The curve matches Planck's formula with a precision that is almost absurd, deviations of less than 1 part in 10,000. This means that the oldest light in the universe, light that has been traveling for 13.8 billion years, carries the fingerprint of Planck's discovery in its spectrum. The quantum hypothesis that a reluctant German professor introduced in 1900 to explain why hot objects glow a particular color is written across the sky. Every microwave photon in the cosmic background is a quantum,
a discrete packet of energy, exactly as Planck described. And together, they paint the most accurate blackbody curve ever observed. A curve that begins its story in a laboratory in Berlin and ends it at the edge of the observable universe. The quantum is everywhere. It was always everywhere. We just needed 6 experiments to see it. Just rest. The questions will keep. The mystery will keep. For now, let the wave function of your thoughts decohere gently into sleep. Let the superposition of the day's worries collapse into a single, quiet state of rest. Breathe in. Breathe out. The atoms in the air you are inhaling were forged in the cores of stars, scattered by supernovae, drifting through interstellar space for billions of years before finding their way into your lungs tonight. Each one of them obeys quantum mechanics. Each one of them is described by a wave function.
Each one of them has no definite position until the moment it interacts with the molecules in your bloodstream. And even then, definite is a word that quantum mechanics uses only reluctantly. You are part of the wave function of the universe, and the wave function of the universe is evolving, right now, smoothly and quietly and deterministically, carrying you along with it. Whatever happens next, whatever branch you find yourself on in the morning, is already encoded in the mathematics. For now,